Hello everyone, hope you are doing good. In this video, I'll be solving the exercise questions of Class 12 Chemistry, Chapter 2, Solutions. So without wasting time, let's directly move into the question. Question number 2.1. Define the term solution. How many types of solutions are formed? Write briefly about each type with an example. So let us answer this question. So we need to define the term solution in the beginning. So solution is nothing but it is a homogeneous mixture of two or more than two components. And we have three different types of solutions. They are gaseous solution, liquid solution and solid solution. We need to explain what are these different types of solutions. So we know solutions are classified based on the solvent that is present in them. So the first classification is gaseous solution. So the solutions in which solvent is a gas is called as a gaseous solution. So here solute can be solid, liquid or gas. So an example for gaseous solution is mixture of oxygen and nitrogen gases. Second type is liquid solutions. So the solutions in which solvent is a liquid is called as a liquid solution. And the solute here can be solid, liquid or gas. Example is a solution of glucose in water. And the third type is solid solution. The solutions in which solvent is a solid. That type of solution we call it as solid solution. Here also solute may be either solid, liquid or gas. Example for solid solution is solution of copper in gold. So this is the answer for question number 2.1. Question number 2.2. Give an example of solid solution in which the solute is a gas. So first of all here we will define what is solid solution. A solution in which solvent is a solid solution. So here the solute is a gas. So example for such a solution is hydrogen gas in palladium. So this is an example for a solid solution where the solute is a gas. 2.3. Define the following terms: mole fraction, molality, molarity and mass percentage. So we will answer one by one. First we will write what is mole fraction. So it is the ratio of number of moles of the component to the total number of moles of all the components that is present in a mixture. So we will write the formula. Mole fraction of a component is equal to the number of moles of the components divided by total number of moles of all the components. So this is the formula for the mole fraction of a component, and this mole fraction is represented by the symbol chi. Now if we consider a binary solution, so means the solution contains two components, and now let us denote the components as A and B. So I'll write let A and B be the components of a binary solution and I'll consider NA and NB as number of moles of A and B. And from this we can write the mole fraction of the individual components. Say for the mole fraction of component A, it is denoted by chi A, and that is equal to, it is number of moles of the component, means it is Na, divided by total moles of all the components, that is sum of Na and Nb. So chi A is equal to Na divided by Na plus Nb. That gives the mole fraction of component A. And for component B, mole fraction is represented as chi B, and the formula here is Nb divided by Na plus Nb. And for a given solution, sum of mole fractions of all the components is 1. And we can write chi A plus chi B is equal to 1. Second term that we need to define here is molality. Molality is the number of moles of solute per kg of the solvent. So the formula is written as molality, represented by small letter alphabet M, is equal to moles of solute divided by mass of solvent in kg. So this gives us molality. So next term we need to define is molarity. So molarity is the number of moles dissolved in 1 liter of the solution. Writing the formula, molarity represented by capital letter M is equal to, it is the number of moles of solute divided by volume of solution in liters. So this is how we define molarity. Moving to the fourth term. The fourth term that we need to define is mass percentage. So mass percentage of a component of a solution is defined as mass of solute in grams present in 100 grams of the solution. So mathematically we can write mass percentage of a component in a solution is equal to mass of the component divided by total mass of the solution into 100. So this gives us mass percentage of the component in the solution. Say for a given solution, if we are asked to determine the mass percentage of the solute, then the formula would be mass of solute divided by total mass of the solution into 100%. Meanwhile, in the same problem, if we are asked to determine the mass percentage of solvent, then it is mass of solvent divided by total mass of the solution into 100. Or it is 100 minus the mass percentage of solute. So if any one of the mass percentage is known, we can obtain the other by subtracting it from 100, because sum of the mass percentage of solute as well as solvent is 100%. Concentrated nitric acid is used in laboratory work is 68% nitric acid by mass in aqueous solution. What should be the molarity of such a sample of acid if the density of the solution is 1.504 gram per ml? So they have given us that 68% nitric acid solution is used. So let me write the 68% nitric acid solution in water, means it's aqueous solution. It means that we have 68 gram of nitric acid in 100 gram of the solution. So we should be finding the molarity. So let me write the formula for molarity in the beginning, represented by capital letter M. So molarity is number of moles of the solute per liter of the solution. So it is moles of solute, means here moles of nitric acid divided by volume of solution in liter. So now we need to find the number of moles of nitric acid. So in order to find number of moles, we need mass of nitric acid, also molar mass of nitric acid. Mass of nitric acid, they have given it as 68 gram. So we will find the molar mass of nitric acid. Molar mass of HNO3 is equal to, we have one hydrogen atom into its atomic mass plus one nitrogen atom into its atomic mass, and we have 3 oxygen atom multiplied by its atomic mass. So the molar mass is 1 plus 14 plus 48, and that is equal to 63 grams per mole. So mass of nitric acid is already given. So we will calculate number of moles of nitric acid. So moles of HNO3 is equal to its mass, that is 68 grams, divided by the molar mass, that is 63 grams per mole, and this is equal to 1.079 moles. In order to find molarity, now we need volume of solution in liter. But this volume is not given to us. Instead, they have given density of the solution. So we have density of solution that is equal to 1.504 gram per ml. And we have mass of the solution, that is 100 grams. So using mass as well as density, we can determine volume of the solution. And therefore, volume of 100 grams of solution, it is nothing but its mass divided by density. So mass is in terms of gram, density is in terms of gram per ml. Grams and grams get cancelled with one another, and we get volume of the solution as 66.49 ml. But in order to find molarity, we need volume in terms of liter. So 1 milliliter is 10 to the power minus 3 liter. So I can write 66.49 into 10 to the power minus 3 liter is the volume of the solution. Now we will substitute the number of moles of HNO3 as well as volume of the solution into the formula for molarity, and we will calculate molarity of the solution. Substituting the values into the formula, molarity is equal to moles of HNO3, that is 1.079 moles, divided by volume of the solution in liter, it is 66.49 into 10 to the power minus 3. So after solving this, we will get the molarity as 16.23 molar. And this is how you can solve this question. Question number 2.5. A solution of glucose in water is labeled as 10% weight by weight. What would be the molality and mole fraction of each component in the solution? If the density of the solution is 1.2 gram per ml, then what shall be the molarity of the solution? So we should be finding molality of the solution as well as mole fraction of both the components, and then we have to find molarity of the solution. So first we shall find molality of the solution. So I'll write the formula first, and then we shall identify what are the things required to substitute into that particular formula, and then we will find them and substitute. Molality is moles of solute per kg of the solvent. So it is divided by mass of solvent in kg. So now we will find moles of the solute, and then we will substitute into the formula. So in the question they have given us it is 100% weight W bar W, that's mass by mass value is given. So 100% of glucose solution it means that we have 100 gram of glucose, sorry, we have 10 grams of glucose in 100 gram of solution. Okay, so from this we can tell that the mass of water or the amount of water is 100 minus 10, and that is equal to 90 grams. Okay, so we have total 100 grams of solution, out of which 10 gram glucose is present and 90 gram water is there. So now we have mass of the solute here. We will calculate molar mass of glucose, and then we will find the moles. Molar mass of glucose. The formula of glucose is C6H12O6, and we will calculate the molar mass now. So it is 6 into atomic mass of carbon plus 12 into atomic mass of hydrogen plus 6 into atomic mass of oxygen. And therefore the molar mass of glucose is 180 grams per mole. So now we will find number of moles of glucose. Moles of glucose is equal to its mass, that is 10 gram, divided by molar mass, that is 180 grams per mole. So after simplifying this we get 0.056 moles. Now we will substitute this value into the expression of molality. So we can calculate molality of the solution, that is capital letter M. It is number of moles of glucose, that is 0.056 divided by mass of solvent in kg. So just now we have calculated mass of solvent is 90 grams. So molality is 0.056 divided by 90. So this 90 is in terms of gram, but we should be substituting the mass of solvent in kg. Remember that. So this 90 grams in terms of kg is 0.09 kgs. So we will be substituting it in terms of kg. So 0.056 moles divided by 0.09 kg, and this is equal to 0.62 mole per kg. That is nothing but 0.62 molal. Now we need to find the mole fractions of each of the components in the solution. So we will find the number of moles of water, and already we have the number of moles of glucose. We will substitute into the formula of mole fraction, and we will calculate mole fraction for glucose as well as water. Number of moles of water is equal to mass of water, that is 90 gram, divided by its molar mass. So molar mass of water is 18 grams per mole. So we have to calculate 90 by 18, and that's equal to 5. So we have 5 moles of water. And the number of moles of glucose already we have calculated, that is 0.056 mole. So I'll just write here N of glucose is 0.056 mole. So now using these two we can calculate mole fraction. So let me write mole fraction of glucose. So this mole fraction is represented by chi. So chi for glucose is number of moles of glucose divided by number of moles of glucose plus number of moles of water. So number of moles of glucose is 0.056 divided by 0.056 plus 5, and this is equal to 0.011. Similarly, we will calculate mole fraction of water. So mole fraction of water, that is chi water, is equal to number of moles of water divided by number of moles of glucose plus number of moles of water, that is 5 divided by 0.056 plus 5, that is equal to 0.989. So this is one way of doing it, by writing the formula. Or the other way, you can determine mole fraction of water. Already I told you that sum of mole fraction of all the components that is present in a solution is 1, which means here chi of glucose plus chi for water is equal to 1. So from this I can write chi for water is 1 minus mole fraction of glucose. So that is 1 minus 0.011, and that's equal to 0.989. So this is the other way how we can calculate the mole fraction for water. And they have given us density and they have asked us to find molarity. Now we shall proceed to find molarity of the solution. To proceed, let me write the formula for molarity. So molarity is number of moles of solute dissolved in 1 liter of the solution, or it is present in 1 liter of solution. So it is moles of solute divided by volume of solution in liter. So solute here means it is glucose. So we have calculated the number of moles of glucose, that is N of glucose. I'll write 0.056 mole. We need to calculate is volume of solution in liter. So we know mass of solution, that is 100 gram. They have given us density, that is 1.2 gram per ml. Mass of solution, we have 100 grams. Using these two, we can find volume of solution. So therefore, volume of 100 gram of solution is equal to its mass, that is 100 gram divided by density. Mass is 100 gram, density is 1.2 gram per ml, that is 83.33 ml. But we need volume of the solution in terms of liter. So 1 milliliter is 10 to the power minus 3 liter. So this is 83.33 into 10 to the power minus 3 liter. Now we will substitute these values into the formula for molarity. So moles of solute M molarity is equal to moles of solute of glucose 0.056 divided by volume of solution in liter, that is 83.33 into 10 to the power minus 3. After simplifying this, we get molarity of the solution as 0.67 molar. Question number 2.6. How many milliliter of 0.1 molar HCl are required to react completely with 1 gram mixture of sodium carbonate and sodium bicarbonate, that is Na2CO3 and NaHCO3, containing equimolar amounts of both? So they have asked us to calculate the milliliter of 0.1 molar HCl which reacts with a mixture of sodium carbonate and sodium bicarbonate and which contains equimolar mixture. Okay, so they have given us the mass of mixture of sodium carbonate, that is Na2CO3, and sodium bicarbonate, NaHCO3, that is equal to 1 gram. Now let us consider mass of sodium carbonate as X. So then what would be the mass of sodium bicarbonate? Since the mixture has mass 1 gram, mass of sodium bicarbonate is 1 minus X. Therefore, mass of NaHCO3, that sodium bicarbonate, is 1 minus X grams. In order to find the amount of HCl that's required to react with this particular mixture, we need to find the number of moles of sodium carbonate as well as sodium bicarbonate. So we will proceed to find that. So in order to find number of moles, we need molar masses of sodium carbonate as well as bicarbonate. So we will find molar mass and then we will find number of moles. So molar mass of sodium carbonate, Na2CO3, is 2 into the atomic mass of sodium, that is 23, plus 1 into atomic mass of carbon, that's 12, plus 3 into atomic mass of oxygen, that is 16. After adding all this, we get molar mass as 106 grams per mole. Now we will find the moles of sodium carbonate, Na2CO3, that is equal to mass by molar mass of sodium carbonate. So mass, we have considered it as X gram. Molar mass is 106 grams per mole. So this is the number of moles of sodium carbonate. Similarly, we will calculate for sodium bicarbonate. Molar mass of NaHCO3 is equal to 1 into atomic mass of sodium plus 1 into atomic mass of hydrogen plus 1 into atomic mass of carbon plus 3 into atomic mass of oxygen, and this is equal to 84 grams per mole. Now we will calculate number of moles of sodium bicarbonate, NaHCO3, that's equal to its mass by molar mass. Mass of NaHCO3 is 1 minus X grams divided by the molar mass, that is 84 grams per mole. Now in the question they have given that the mixture is equimolar, means number of moles of sodium carbonate is equal to the number of moles of sodium bicarbonate. So therefore, if I denote number of moles of sodium carbonate as 1 and number of moles of sodium bicarbonate as 2, I can write 1 is equal to 2 because we have equimolar mixture. So therefore I can write x by 106 is equal to 1 minus x divided by 84. So this I can rearrange and write as 84x is equal to 106 minus 106x. Rearranging this equation, we can write 84x plus 106x is equal to 106. 84 plus 106 is 190x is equal to 106, and therefore x is 106 divided by 190, and that is equal to 0.5579. Okay, we have considered x as mass of sodium carbonate. So now using this value of x, we can find what is the mass of sodium carbonate as well as bicarbonate, and we can find the number of moles. Moles of sodium carbonate is x divided by its molar mass 106. So x is 0.5579 divided by 106, and that is equal to 0.0053. Similarly, we can calculate the moles of sodium bicarbonate. So NaHCO3 is equal to 1 minus x divided by 84. 1 minus 0.5579 divided by 84. And this is equal to 0.0053 moles. So we are obtaining number of moles are same because they are present in equimolar amounts. So now we have found out the number of moles of sodium carbonate as well as sodium bicarbonate. Using this number of moles, we can calculate the number of moles of HCl that is required to neutralize them, and we can calculate it in terms of volume. So here we will write the chemical reaction corresponding to the reaction of sodium carbonate as well as bicarbonate with HCl. So when acid reacts with metal carbonates or bicarbonate, we get the corresponding metallic salt along with water and liberation of carbon dioxide. So the corresponding reaction is HCl plus Na2CO3. So here we get the salt NaCl plus water and carbon dioxide. So balancing this reaction, I should be writing 2 NaCl and 2 HCl. So this means that 2 moles of HCl reacts with 1 mole of sodium carbonate. Now we'll write the reaction with sodium bicarbonate, HCl plus NaHCO3. Again the products are same. It is the salt, sodium chloride, water and carbon dioxide. So this equation is already balanced. So from this I can write 1 mole of HCl reacts with 1 mole of sodium bicarbonate. Now I'll write these two reactions as 1 and 2. So from the chemical equation 1, we can tell that 2 moles of HCl reacts with 1 mole of sodium carbonate. But now in the mixture we have 0.0053 moles of sodium carbonate. So what would be the number of moles of HCl that is reacting? So how we can find? So we have 0.0053 mole of sodium carbonate. How much is the HCl that is reacting with it? So just cross multiplication, 0.0053 into 2, and that is equal to 0.0106 moles. So you can tell 0.0106 moles of HCl reacts with 0.0053 moles of Na2CO3. Similarly, from the second chemical equation, I can tell that 1 mole of HCl reacts with 1 mole of sodium bicarbonate, NaHCO3. So, but in the reaction mixture, we have 0.0053 mole of sodium bicarbonate. So, how much HCl would react with it? So, cross multiplying this, we get 0.0053. So, I can write 0.0053 moles of HCl reacts with 0.0053 mole of NaHCO3. But now we have mixture of sodium carbonate and sodium bicarbonate. And therefore, total moles of HCl required to react is sum of 0.0106 and 0.0053 moles, and that is equal to 0.0159. So this means that we require 0.0159 moles of HCl to react with sodium carbonate and sodium bicarbonate mixture. Now we need to find this quantity of HCl in terms of milliliters. Let us do that now. So in the question they have given us, we have 0.1 molar HCl solution. So 0.1 molar means that we have 0.1 mole of HCl in 1000 ml of the solution. So this is what is molarity means. It is the moles of solute per liter of the solution. So to make it simple, I can write we have 0.1 moles of HCl in 1000 ml of solution. But what we require is 0.0159 moles of HCl. So how many mLs would consist 0.0159 moles? Just cross multiplication. 0.0159 into 1000 ml. So this 0.0159 is mole divided by 0.1 mole. So this mole and mole get cancelled. Whatever the answer we get is in terms of milliliter. Just by simplifying the numerical values, we get it as 159. So we require 159 ml of 0.1 molar HCl solution to completely react with 1 gram equimolar mixture of sodium carbonate and sodium bicarbonate. So this is how we can answer this particular question. Question number 2.7. A solution is obtained by mixing 300 gram of 25% solution and 400 gram of 40% solution by mass. Calculate the mass percentage of resulting solution. So we are asked to find mass percentage of the solution. Means we have to find mass percentage of solute as well as mass percentage of the solvent. So we have the formula mass percentage of component in a solution is equal to mass of the component divided by total mass of the solution into 100. So this gives us mass percentage. So we need mass of solute as well as mass of solvent in order to find the mass percentage of solute as well as solvent. Now let us find it. So they have given that the solution is obtained by mixing 300 gram of 25% solution and 400 gram of 40% solution. So total mass of solute So here we have 25% of 300 gram. So it is 25 by 100 into 300 gram. Also we have 40 grams of 40% solution. So means we have 40 by 100 into 400. So simplifying this, we get 75 plus 160 and this is equal to 235 gram. So this is total mass of solute. Now if we consider the total amount of solution, it consists of 300 gram of 25% solution and 400 gram of 40% solution. So total mass of the solution is 300 gram plus 400 gram and that's equal to 700 gram. So using these data, now we will find the mass percentage of solute as well as solvent. So first, mass percentage of solute. So that is equal to mass of solute divided by total mass of solution into 100. So mass of solute we have calculated, it is 235 grams and divided by mass of the solution, that is 700 grams into 100 and this is equal to 33.57 percentage. And now we have to calculate mass percentage of the solvent. So using formula we can solve, but we are not provided with mass of the solvent, right? So what we can do, mass percentage of solvent is nothing but 100 minus mass percentage of solute. This is equal to 100 minus 33.57 and that's equal to 66.43 percentage. So now we have found out the mass percentage of the solution. That is, mass percentage of solute is 33.57% and mass percentage of solvent is 66.43%. Question number 2.8. An antifreeze solution is prepared from 222.6 gram of ethylene glycol, C2, H6O2 and 200 grams of water. Calculate the molality of the solution. If the density of the solution is 1.072 gram per ml, then what shall be the molarity of the solution? So we need to find molality of the solution in the beginning and then using density we have to find molarity of the solution. So let me write the formula for molality. Molality is moles of solute per kg of the solvent, means mass of solvent in kg. So we need to find number of moles of solute. Let us do that. So moles of ethylene glycol is its mass by molar mass. So mass they have given 222.6 grams and its molar mass we need to calculate. We have 2 carbon, so 2 into 12 plus 6 into hydrogen and 2 oxygen atom. So we have 222.6 grams divided by 62 grams per mole, 3.59 moles. In order to calculate molarity, molality, we need mass of solvent in kg. So they have given, we have 200 gram of water. So mass of solvent, that is 200 grams. So we need to convert it into kg. So we have to divide it by 1000. This gives us mass in kg. So we have 0.2 kgs. So now substituting into the formula, molality is equal to number of moles, that is 3.59 moles divided by 0.2 kg. And therefore the molality of the solution is 17.95 molar. Now we need to determine molarity of the solution. So let us write the formula. Molarity is number of moles of solute per liter of the solution. So moles of solute divided by volume of solution in liters. So moles of solute we have already determined, and that is 3.59 moles. Now we need to determine volume of solution in liter. So we will calculate volume of solution in liter and we will substitute into the formula of molarity. The total mass of solution is the sum of mass of solute as well as mass of solvent. So ethylene glycol they have given 222.6 gram and water they have given it as 200 gram. So the total mass of the solution is 422.6 grams. But we need the volume of solution in liters. In order to calculate that, they have given us density of the solution. So density of solution they have given it as 1.072 gram per ml. And therefore, volume of solution is equal to its mass by density. So the mass here is 422.6 grams. Density is 1.072 gram per ml. Simplifying this, we get 394.22 ml is the volume of the solution. But we need volume in terms of liter. So this is 394.22 into 10 to the power minus 3 liter. Now we will substitute this into the formula for molarity. So molarity is number of moles of solute, that is ethylene glycol, it is 3.59 moles divided by volume of solution in liters, that is 394.22 into 10 to the power minus 3 liter. And this is equal to 9.11 mole per liter, that is molarity. Question number 2.9. A sample of drinking water was found to be severely contaminated with chloroform, that is CHCl3, supposed to be a carcinogen. The level of contamination was 15 ppm by mass. Express this percent by mass. Second, determine the molality of chloroform in the water sample. So we need to express 15 ppm in percent by mass. So 15 ppm, that is parts per million. It means we have 15 parts per million. So million means 10 to the power 6. So we have 15 parts per million of the solution. Means mass of solute here is 15 grams and mass of solvent is 10 to the power 6 grams. So into 100 will give us mass percentage. So the mass percentage is 15 gram divided by 10 to the power 6 into 100. And this is equal to 1.5 into 10 to the power minus 3 percentage. So 15 ppm means it is 1.5 into 10 to the power minus 3 percentage. Now secondly, they have asked us to determine molality of chloroform. So let me write the formula. Molality is moles of chloroform divided by mass of solvent, that is water here, in kg. So we need to find moles of chloroform. So in order to find that, we need its mass and molar mass. So let us calculate molar mass of chloroform. Molar mass of CHCl3. So it is 1 carbon and we have 1 hydrogen and we have 3 chlorine atoms. So the molar mass of chloroform is 119.5 grams per mole. So now we will calculate the number of moles of chloroform. So moles of CHCl3 is equal to its mass, that's what we have, 15 gram, divided by molar mass 119.5, and this is equal to 0.1252 moles. So now we need mass of solvent in terms of kg. After finding that, we will substitute into the formula of molality. So it's told that we have 15 ppm chloroform in solution. It means that we have 15 gram of chloroform in 10 to the power 6 gram of solution. So from this we can calculate the mass of solvent. So means we have 10 to the power 6 minus 15 gram of water is there in it. So when compared to 10 to the power 6, 15 is very much smaller. So I can consider this as equivalent to 10 to the power 6 gram of water. So this 10 to the power 6 gram is the mass of solution. Now this is in terms of gram. We should be writing it in terms of kg. So we have to divide it by 1000. So it is 10 to the power 6 divided by 1000 grams of water we have. And that's equal to 10 to the power 3 kg of water. Molality is equal to moles of chloroform, that is 0.1255 divided by mass of solvent in kg, that is 10 to the power 3 kg, and therefore we get the answer as 1.26 into 10 to the power minus 4 mole per kg. So this is nothing but 1.26 into 10 to the power minus 4 molar. Question number 2.10. What role does the molecular interaction play in a solution of alcohol and water? So we will understand this. We have alcohol and water. If you consider the interaction between alcohol and alcohol. So in a solution of alcohol, you have alcohol molecules that they will interact with them. And if you consider water, the interaction between water molecules. So they have hydrogen bonding between them. So if you consider alcohol, we have CH3OH, CH3OH. So there is hydrogen bonding present between oxygen of one alcohol and hydrogen of other alcohol molecule. Similarly, if you consider water molecules, you have hydrogen bonding between water molecules. Oxygen atom of one molecule of water and hydrogen of the other molecule of water. So we have hydrogen bonding. So these hydrogen bonding that is present in alcohol-alcohol and water-water interaction are very much stronger. When you mix alcohol and water, so we will have interaction between alcohol molecule as well as water molecule. So if I write CH3OH and water molecule H2O, there will be hydrogen bonding between hydrogen of alcohol as well as oxygen of water molecule, or oxygen of alcohol molecule and hydrogen of water molecule. So this is also hydrogen bonding. So but the hydrogen bonding between alcohol and alcohol as well as water and water is more strong than that of the hydrogen bonding that is present in alcohol-water interaction. So because of this weak interaction, alcohol and water, when they are mixed together, their bond becomes weak. So because of this weak bond, these molecules can easily escape. So that's what we call their vapor pressure will increase. So because of this increase in the vapor pressure, boiling point of the solution will decrease. So this is what is the interaction affects the alcohol, water when they are mixed together. So the answer is, in pure alcohol and water, the molecules are held tightly by strong hydrogen bonding. The interaction between molecules of alcohol and water is weaker than that of alcohol-alcohol and water-water interaction. As a result, when alcohol and water are mixed, the intermolecular interactions become weaker and molecules can easily escape. This increases vapor pressure of the solution, which in turn lowers boiling point of the resulting solution. Moving to question number 2.11. Why do gases always tend to be less soluble in liquids as the temperature is raised? Now the answer for this question is that solubility of the gases in liquids decreases with increase in temperature. We need to explain this, right? We know that dissolution of gases in liquids is exothermic process. Exothermic means heat is liberated during the reaction. So that is represented by the reaction here. Gas plus liquid, there is an equilibrium that is existing between the solution. This equilibrium is dynamic equilibrium. Dynamic means the equilibrium is shifting from left side to right side or right side to left side. The reaction is not constant. Some changes is happening in that. Okay. So now the dilution process involves dynamic equilibrium, as I told. So hence we can use Le Chatelier principle here. We told that the reaction is already exothermic, means heat is getting liberated. Now if you supply more temperature, heat will also increase. So because of this increase in the temperature, system always try to decrease the temperature so as to balance. So the equilibrium will be shifting towards the left hand side. So because of which the solubility of the gas in a liquid will decrease. So this is how we can explain the decrease in solubility of gas in a liquid when temperature is increased. Question number 2.12. State Henry's law and mention some important applications. So the statement of Henry's law is that partial pressure of a gas in the vapor phase is proportional to mole fraction of the gas in solution. So if we write P as partial pressure of gas in the vapor phase and chi as the mole fraction of the gas, then we can write Henry's law as P is equal to KH into chi, where KH is Henry's law constant. So this is this statement. Now we need to mention its application. So coming to the application parts of Henry's law. So the bottles of soft drinks or soda water is sealed under high pressure to increase the solubility of carbon dioxide. And the second application is that in terms of scuba divers. So scuba divers carries a oxygen cylinder with them. So this is because this oxygen is diluted and this is containing helium. So if we don't use this oxygen cylinder, what will happen? As these dye will go underwater, the pressure will be more inside the water. Because of increase in the pressure, the gases are highly soluble. So the air that we breathe in underwater, so that consists of all other gases that are dissolved in it. So nitrogen, since it is present in larger quantity in air, this nitrogen is also highly soluble. As these divers come up, what will happen? The solubility of these gases will decrease because of the decrease in the pressure. As a result, they will come out as bubbles. So this air that is dissolved in the blood, now nitrogen gas is coming out in the form of bubbles, and that causes the nitrogen bubbles in the blood, and this results in the blockage of capillaries, and this results in a medical condition known as bends. So in order to avoid this, scuba divers carry oxygen cylinder with them, and this oxygen that is diluted with helium, and lesser amount of nitrogen is present in that. The third application is that concentration of oxygen is lower in blood and tissues of the people. They are living at high altitudes such as climbers. So because of this high altitude, partial pressure of oxygen becomes lesser than that of the ground level, and low blood oxygen causes these climbers to become weak and disables them from thinking clearly, and such a medical symptom we call it as anoxia. So in all these different cases, Henry's law is applied. Depending on the marks that is allotted for this particular question in your examination, you can choose the applications which you can write. Question number 2.13. The partial pressure of ethane over a solution containing 6.56 into 10 to the power minus 3 grams of ethane is 1 bar. If the solution contains 5 into 10 to the power minus 2 grams of ethane, then what shall be the partial pressure of the gas? So here we are asked to find the partial pressure for ethane gas, and they have given us the quantity of ethane that is present in that particular solution. So we have two different cases. First, they have given partial pressure of ethane over solution containing 6.56 into 10 to the power minus 3 gram. Its partial pressure is 1 bar. So this is first part of the question, and in the second part they have asked us to calculate partial pressure of ethane in some other solution. Okay. So here we will make use of Henry's law. P is equal to KH into chi. Chi is the mole fraction. So now in first case, we will substitute all the data that is given. So in order to calculate mole fraction, we need to find number of moles of solute as well as the solvent. Okay. So in order to find the value of chi, let us first find the molar mass of ethane. Ethane is C2H6. So its molar mass is 2 into 12 plus 6 into 1. So it's 24 plus 6, which is equal to 30 grams per mole. Also, mass of ethane that is given. So we can calculate number of moles. So mass of ethane here is 6.56 into 10 to the power minus 3 grams. So number of moles, that's equal to mass is 6.56 into 10 to the power minus 3 gram divided by the molar mass is 30 gram per mole, and therefore the number of moles of ethane that is present here is 2.187 into 10 to the power minus 4 moles. Now we shall consider the number of moles of solvent as X. Because it is not given, we will consider it as X. So now using all this data, we can substitute it into the formula P is equal to KH into X. So they have given partial pressure as 1 bar. So substituting this into formula, we have 1 is equal to, KH is what we don't know, and chi, its number of moles of ethane, 2.187 into 10 to the power minus 4 divided by 2.187 into 10 to the power minus 4 plus x. So since x is much greater than 2.187 into 10 to the power minus 4, this denominator we can consider it as equivalent to x. So I can write 1 is equal to KH into 2.187 into 10 to the power minus 4 divided by x. Rearranging this equation, we can write Henry's law constant as x by 2.18 into 10 to the power minus 4 bars. Now, the mass of ethane they have given it as 5 into 10 to the power minus 2 grams. And therefore, moles of ethane is equal to 5 into 10 to the power minus 2 grams divided by 30 grams per mole. And this is equal to 1.67 into 10 to the power minus 3 moles. Now, we will use Henry's law. P is equal to KH into chi. So, where KH is what we have found out considering the previous case. That is x divided by 2.18 into 10 to the power minus 4. And mole fraction is number of moles of ethane, that's 1.67 into 10 to the power minus 3 divided by 1.67 into 10 to the power minus 3 and that of the solvent, that is x. So since x is much greater than 1.67 into 10 to the power minus 3, we can write this as 1.67 into 10 to the power minus 3 divided by x. And that is multiplied by x by 2.18 into 10 to the power minus 4. So x and x gets cancelled. We have to just simplify the remaining numbers and we get partial pressure as 7.636 and the unit is bar. And therefore, the partial pressure of the gas will be 7.636 bars. Question number 2.14. What is meant by positive and negative deviations from Raoult's law? And how is the sign of delta H of solution is related to positive and negative deviations from Raoult's law? So before we tell positive and negative deviations from the Raoult's law, we shall state what is Raoult's law. According to Raoult's law, the partial vapor pressure of each volatile component in any solution is directly proportional to its mole fractions. Now, those solutions which obey Raoult's law over the entire range of concentration, we call it as ideal solutions. And those solutions which do not obey Raoult's law, we call it as non-ideal solutions. So, these non-ideal solutions can have either higher or lower vapor pressures than the predicted. So, this is what we call it as deviation. So, if the vapor pressure is higher, then those solutions exhibit positive deviation, and if the vapor pressure is lower, then the solutions are said to exhibit negative deviations from the Raoult's law. So it is the non-ideal solutions that exhibit positive and negative deviations from Raoult's law. So here you can see from this graph, the first graph is representing positive deviation from the Raoult's law. And the second graph is represented negative deviation from the Raoult's law. So here you can see this was the actual pressure that was expected to be observed, but the vapor pressure of the solution is higher than that. So that is positive deviation. Here you can see this dotted straight line represents the actual pressure that was expected, but the vapor pressure of the solution was found lower than that. So this is showing a negative deviation from Raoult's law. Now, answering to the question related to the sign of heat of solution. In case of ideal solution, the enthalpy of mixing of pure components for forming the solution is 0. That is, delta H of solution is 0. But in case of non-ideal solutions, the one which is showing positive or negative deviation. So in case if it is showing positive deviation, then absorption of heat is taking place, that it is endothermic reaction. So delta H of solution is positive. If the solutions are showing negative deviation, there is evolution of heat that is taking place, which is exothermic reaction, and therefore delta H of the solution is negative. Question number 2.15. An aqueous solution of 2% non-volatile solute exerts a pressure of 1.004 bar at the normal boiling point of the solvent. What is the molar mass of the solute? In the question, it's given that we have 2% aqueous solution of non-volatile solute. So means if we consider the solution, we have 2% non-volatile solute in it. Means out of 100 gram of solution, 2 grams solute is present, and the solute is non-volatile. It means that we have 100 minus 2 grams of solvent, that is water here, since it is aqueous solution. So we have 98 gram of water. So these non-volatile solute will undergo vaporization, and these vapors exerts pressure. So that is what we call it as vapor pressure. So the vapor pressure of the solution at the normal boiling point of water, they have given it as 1.004 bar. So we will just write these things. We have mass of solute. Let us denote this as W2, which is nothing but 2 grams. Also we have mass of solvent, that is water. We'll denote it as W1, which is 98 grams. Also we are given with the vapor pressure of the solution. So I'll write Vp, that is vapor pressure of the solution at normal boiling point of water. At the normal boiling point of solvent, that is water. So they have given it as 1.004 bar. So this vapor pressure, we will denote it as P1. And we know that vapor pressure of pure water, that is P1 naught, which is equal to 1.013 bar. Also we shall write the molar mass of solvent. So that is water. Molar mass of water. We'll denote it as M1, which is equal to 18 gram per mole. So how do we get 18 grams per mole? We have 2 hydrogen and 1 oxygen. So it is 2 into atomic mass of hydrogen and 1 into atomic mass of oxygen. So it is 2 into 1 plus 1 into 16. So when we add together, we get it as 18 grams per mole. So we are asked to calculate the molar mass of solute. So let that be M2. So molar mass of the non-volatile solute, M2, we have to find it. So we can use Raoult's law here. So I'll write from Raoult's law. we have P1 naught minus P1 divided by P1 naught, which is equal to weight of solute into molar mass of the solvent divided by molar mass of the solute into mass of the solvent. Now let us substitute all the given terms into the expression of Raoult's law, and we will simplify it to get molar mass of the solute, that is M2. P1 naught is 1.013 minus P1 1.004 divided by P1 naught is 1.013, which is equal to W2 into M1. W2 is 2, which is the mass of the non-volatile solute, and W1 is molar mass of water, that is 18 gram per mole. M2 is what we have to find, and W1 is 98. So we will simplify this. 0.009 divided by 1.013, which is equal to 2 into 18 divided by 98 M2. So rearranging, we can write M2 is equal to 1.013 into 2 into 18 divided by 0.009 into 98. Further simplification, on numerator we have 36.468 divided by 0.882. This is equal to 41.346, which approximately we can write it as 41.35 grams. And therefore, the molar mass of the non-volatile solute in that given solution is 41.35 gram per mole. Question number 2.16. Heptane and octane form an ideal solution. At 373 Kelvin, the vapor pressures of the two liquid components are 105.2 kilopascal and 46.8 kilopascal respectively. What will be the vapor pressure of a mixture of 26 gram of heptane and 35 gram of octane? Here in the question, we are provided with vapor pressures of pure heptane and octane. So that is 105.2 kilopascal and 46.8 kilopascal. And they have given us mass of these heptane and octane required to prepare a particular mixture, and we are asked to find vapor pressure. So in order to find this vapor pressure, initially we will find the partial pressures of 26 gram of heptane and 35 gram of octane individually. So when we sum up this, we get the total vapor pressure of the mixture. So in order to find the partial pressure, we will use vapor pressures of these two components in its pure form, and using the mass given, we will find the number of moles, and then we will substitute it into the formula. Partial pressure of the component is the product of its mole fraction multiplied by vapor pressure of the pure component. So using these two formula, we will individually find the partial pressures of heptane and octane. Then we will find the total vapor pressure of the mixture. We will start to solve. Initially, we will list what are the things that is given to us in the question, and we will proceed with the solution. We are provided with vapor pressures of heptane and octane. In the pure form, we will write vapor pressure of heptane let me denote this as P1 naught, which is equal to 105.2 kilopascal. And we have vapor pressure of octane. Let me denote this as P2 naught, which is equal to 46.8 kilopascal. We will calculate the molar mass of heptane as well as octane. Molar mass of heptane. We will denote this as M1. So in order to calculate the molar mass, we need to write the formula first, right? So it is heptane. An means it is an alkane. Hept means we have 7 carbon atoms. So the general formula for alkane is CnH2n plus 2. I hope you remember this. So N value is 7. So this is C7H 2 into 7 plus 2. So the formula is C7H14 plus 2. And this is C7H16. So this is heptane. We will calculate the molar mass. We have 7 carbon atom into its mass, that is 12. And we have 16 hydrogen atom into 1, that is the atomic mass. So this comes out to be 100 gram per mole. Together we will calculate number of moles. So number of moles of heptane. Let me denote this as N1. So number of moles is its mass divided by molar mass. So mass of heptane in the mixture, that is given to us as 26 gram, divided by its molar mass is 100 grams per mole, and so the number of moles is 0.26 moles. Similarly, we will calculate the molar mass of octane and the number of moles as well. So molar mass is M2. So we shall write the formula for octane. So we have 8 carbon atoms. So it is C8H 2 into 8 plus 2. C8H16 plus 2. C8H18 is the formula of octane. So we have 8 carbon into its atomic mass, that is 12. 18 hydrogen atoms into its atomic mass, and this is equal to 114 grams per mole. Number of moles of octane. Let me denote this as N2, which is its mass by molar mass. So we have 35 gram divided by its molar mass is 114 gram. This comes out to be 0.31 moles. So now we have calculated the number of moles of heptane as well as octane using these number of moles as well as the vapor pressure of the pure components of heptane as well as octane. Now we will calculate their mole fractions. Mole fraction is represented by chi. So for one component, say for first component chi 1, the mole fraction is number of moles of component 1 divided by sum of number of moles of component 1 as well as component 2. Using this formula, now we will calculate the mole fractions for heptane as well as octane by substituting the relevant values. Mole fraction of heptane denoted as chi 1. So that is equal to N1 divided by N1 plus N2. So I have taken values here inside this box. So we will substitute chi 1 is equal to N1 is 0.26 0.26 divided by 0.26 plus 0.31. Upon simplifying this, we get mole fraction of heptane as 0.456. So using this value of mole fraction, we can calculate the mole fraction of octane. We know that the mole fraction of all the components will add up to 1. So mole fraction of octane chi2 is nothing but 1 minus chi1. So that is 1 minus 0.456, and this is equal to 0.544. So now we have calculated mole fractions of both the components in the solution. Now we shall calculate partial pressure for heptane as well as octane. So partial pressure of heptane, that is P1, is equal to chi1 into P1 naught. So chi1 is 0.456 into its P1 naught is 105.2 kilopascal, and this is equal to 47.97 kilopascal. Similarly, partial pressure of octane, that is P2, is equal to chi2 into P2 naught. Chi2 is 0.544, P2 naught is 46.8 kilopascal, and this is equal to 25.46 kilopascal. So we have obtained the partial pressures of heptane as well as octane. So the total vapor pressure of the solution is sum of these two. Vapor pressure of the solution nothing but I can write it as P total, which is equal to P1 plus P2. So P1 is 47.97 kilopascal, P2 is 25.46 kilopascal. When we add these two values, we get 73.43 kilopascals. So the total vapor pressure of the solution is 73.43 kilopascal. Question number 2.17. The vapor pressure of water is 12.3 kilopascal at 300 Kelvin. Calculate vapor pressure of 1 molar solution of a non-volatile solute in it. Vapor pressure of pure water is given. I'll denote this as P1 naught, which is equal to 12.3 kilopascal, that is at 300 Kelvin. And they have given us it is 1 molar solution of the solute in water. So this means that 1 mole of solute is dissolved in 1 kg of water. So this 1 kg means it is 1000 grams of water. Using this data, we can calculate the mole fraction of solute. So in order to do that, say let me write mole fraction of solute. I'll denote this as chi2, that is nothing but N2 divided by N1 plus N2. So here chi2 is mole fraction of solute. N1 is number of moles of water. N2 is number of moles of solute. So we will calculate N1 and N2 and then we will calculate the mole fraction of solute. N1 is the number of moles of water. So we have mass of water divided by its molar mass. So that gives us number of moles for water. So since they have given this 1 molar solution, so we know we have 100 grams of water in it. 1000 grams of water in it divided by molar mass of water, that is 18 grams per mole. So simplifying this, we get the number of moles of water as 55.56 moles. Now N2, it is the number of moles of solute. So 1 molar solution, it means that 1 mole of solute is there. So N2 is nothing but it is 1 mole. So we will substitute into the expression of chi2, that is N2 divided by N1 plus N2. So N2 is 1 divided by N1 is 55.56 plus 1. So upon simplifying this, we get the mole fraction of solute as 0.0177. What we need to find here is the vapor pressure of this particular solution. So this can be found out by the equation P1 naught minus P1 divided by P1 naught is equal to chi2. So using this relation, now we will find the vapor pressure of the solution. P1 naught is 12.3 kilopascal minus P1 is what we have to determine. P1 naught is 12.3, that is equal to chi2, which is 0.0177. We'll simplify this. 12.3 minus P1 is equal to 0.0177 into 12.3. So this is 12.3 minus P1, which is equal to 0.2177. So from this we can write P1 is equal to 12.3 minus 0.2177, and this is equal to 12.0823. So approximately I can write this as 12.08 kilopascal. So the vapor pressure of the solution is 12.08 kilopascal. You can note here that the vapor pressure of the solution is less than that of the pure solvent. Question number 2.18. Calculate the mass of a non-volatile solute whose molar mass is 40 gram per mole, which should be dissolved in 114 gram of octane to reduce its vapor pressure to 80%. So we should be calculating the amount of solute which we have to add into 114 gram of octane. When this solute is added, vapor pressure of octane will be reduced to 80%. So we will consider the vapor pressure of pure octane as P1 naught. So let the vapor pressure of pure octane be P1 naught. So when adding the non-volatile solute, vapor pressure is reduced to 80%. So after dissolving non-volatile solute, vapor pressure is reduced to 80%. So this means now the vapor pressure is 80% of P1 naught, which is 80 by 100 into P1 naught. That is 0.8 times that of P1 naught. So this value gives us the vapor pressure of the solution. Because after adding the solute, vapor pressure has been decreased. Initially it was P1 naught. After adding the non-volatile solute, the pressure was 0.8 P1 naught. And we are given with molar mass of the solute. So let me write that. Molar mass of the non-volatile solute that is 40 grams per mole. And they have given us the weight of octane. So mass of octane is given to us, that is W1, which is 114 gram. So we can calculate the molar mass of octane from its formula. So molar mass of octane, W1, we will calculate. Octane is an alkane with 8 carbon atom. So its formula is C8H2 into 8 plus 2. So it is C8H18. So molar mass is 8 into 12 plus 18 into 1. And this is equal to 114 grams per mole. Here we will use the relation P1 naught minus P1 divided by P1 naught, which is equal to W2 into M1 divided by M2 into W1. Now we will substitute all the datas into this particular equation and we will find the mass of solute that is required to decrease the vapor pressure to 80%. Substituting the values, P1 naught is P1 itself. P1 naught minus P1 is 0.8 P1 naught divided by P1 naught, which is equal to W2 is what we have to find. So we will write it as such. M1 is 114 divided by M2, that is 40, and W1 is 114. Simplifying this, P1 naught minus 0.8 P1 naught is 0.2 times P1 naught divided by P1 naught, which is equal to W2 divided by 40. So this P1 naught and P1 naught cancels here. So we have W2 is equal to 40 into 0.2 and this is equal to 8 and the unit is grams. So we have to add 8 grams of non-volatile solute to decrease the vapor pressure into 80% of the original value. Question number 2.19. A solution containing 30 gram of non-volatile solute exactly in 90 gram of water has a vapor pressure of 2.8 kilopascal at 298 Kelvin. Further, 18 gram of water is then added to the solution and the new vapor pressure becomes 2.9 kilopascal at 298 Kelvin. Calculate, first one, molar mass of the solute. Second, vapor pressure of the water at 298 Kelvin. So when we go through the question, we can clearly make out that two different cases have been given to us. First is that 30 gram of non-volatile solute is dissolved in 90 gram of water and its vapor pressure is 2.8 kilopascal. So to the same solution, again we are adding 18 grams of water. Okay, so the quantity of solute is 30 gram itself, but to the 90 gram of the water which we had already had the solution, we are adding 18 gram of water. Now the vapor pressure becomes 2.9 kilopascal. Okay, so these are the two situations that they have given to us. We will write the corresponding equation and then from that we will find molar mass of the solute. Once we calculate molar mass of the solute, we can easily determine vapor pressure of the water at the given temperature. So we will proceed with the solution. We will consider molar mass of the solute which we have to determine. Okay, we will consider this as M2. And we will consider vapor pressure of water as P1 and we need to find these two values. Since we are provided with the masses of solute as well as that of the solvent, now we will use the relation P1 minus P1 divided by P1 which is equal to N2 divided by N1 plus N2. So here now P1 is the vapor pressure of the solution. P1 already I have told it is vapor pressure of pure water. N2 is number of moles of solute. N1 is number of moles of water. So we will calculate what are these N2 and N1. So I told two different cases we have. So in the first case, P1 is the vapor pressure of solution that is given to us as 2.8 kilopascal. So the number of moles of solute we need to calculate. So N2 is mass of solute divided by its molar mass. So mass of the solute is 30 gram divided by molar mass of the solute, which we don't know and we have considered it as M2. So this is 30 by M2 gram per mole. And we need to calculate number of moles of water N1. So it is its mass divided by molar mass. So mass of water, it is given as 90 gram. So it is 90 gram divided by molar mass, that is 18 grams per mole. Simplifying this, we get number of moles of water and that is equal to 5 moles. We shall substitute the values of P1, N1 and N2 into this particular relation that I have highlighted here, and we shall obtain an equation in terms of molar mass of the solute. P1 that is taken as P1 itself, we have to calculate it. Minus P1 is 2.8 kilopascal divided by P1 which is equal to N2 which is 30 divided by M2 divided by N1 is 5 moles and N2 is 30 divided by M2. We will simplify this. P1 divided by P1 it is 1 minus 2.8 divided by P1 which is equal to, numerator we will write as such, it is 30 divided by M2. Denominator we will simplify. So taking LCM, denominator we get M2. So this is 5M2 plus 30. So M2 in the numerator and M2 in the denominator gets cancelled. And hence we have 30 divided by 5M2 plus 30 which is equal to 1 minus 2.8 divided by P1. We shall further simplify this. So I'll bring this 30 divided by 5 by M2 plus 30 to one side and P1 term to the other side. So I can write 2.8 divided by P1 is equal to 1 minus 30 divided by 5M2 plus 30. So we shall take an LCM and we can simplify this. 2.8 divided by P1. So the LCM here would be 5M2 plus 30. And on the numerator we have 5M2 plus 30 minus 30. plus 30 and minus 30 gets cancels with one another. From this I can write 2.8 divided by P1 naught is equal to 5m2 divided by 5m2 plus 30. So we cannot simplify this further, and let me denote this as equation 1. Now we will consider the second statement, that is they have told us further 18 gram of water is added into the solution and new vapor pressure has been given. We will consider that, and a similar equation as that of equation 1 we will obtain. So from those two equations we can calculate what is M2. So now I can write, after addition of 18 gram of water, mass of water will become 90 gram plus 18 gram. So that is equal to 108 grams. So now in this case they have given that vapor pressure of the solution will become 2.9 kilopascal. So we can calculate number of moles of water. So N1, it is mass of water 108 divided by its molar mass 18 gram per mole, and the number of moles of water is 6 moles here. Since we have not changed anything with respect to the mass of solute, so number of moles of solute will remain same as that in the previous case. It is its mass 30 gram divided by its molar mass, which we have considered it as M2. Same as in the previous case, we will substitute all these values into the expression P1 naught minus P1 divided by P1 naught, which is equal to N2 divided by N1 plus N2. Substituting the values into the equation, P1 naught minus P1 is 2.9 kilopascal divided by P1 naught. This is equal to N2, that is 30 divided by M2 divided by N1 plus N2. N1 here is 6 moles, N2 is 30 divided by M2. So simplifying this, P1 naught divided by P1 naught is 1 minus 2.9 divided by P1 naught, which is equal to 30 divided by M2, and taking LCM in the denominator, it is 6M2 plus 30. M2 and M2 get cancels with one another, and so we can write 1 minus 2.9 divided by P1 naught, which is equal to 30 divided by 6M2 plus 30. Further rearranging and simplifying, we can write this as 2.9 divided by P1 naught, which is equal to 1 minus 30 divided by 6M2 plus 30. Taking LCM and simplifying, 6M2 plus 30. In the numerator we have 6M2 plus 30 minus 30. So we have 2.9 divided by P1 naught, which is equal to 6M2 divided by 6M2 plus 30. So we will denote this as equation 2. Now we will divide equation 1 by equation 2, from which we can get the molar mass of the solute. So here I have equation 1 and equation 2. Now we shall divide left hand side of equation 1 by equation 2 and right hand side of 1 by equation 2. So I'll write dividing equation 1 by equation 2. So I can write 2.8 divided by P1 naught. This whole thing is divided by 2.9 by P1 naught. And on the right hand side we have 5m2 divided by 5m2 plus 30. And this whole thing is divided by the right hand side of equation 2. So I can write the reciprocal multiplied to this term. So this is 6m2 plus 30 divided by 6m2. We'll simplify this. P1 naught and P1 naught gets cancelled. Here this m2 and this m2 gets cancelled. So you can write 2.8 divided by 2.9 is equal to 5 into 6m2 plus 30 divided by 5m2 plus 30 into 6. By cross multiplying this, we can write 2.8 into 6 into 5m2 plus 30 is equal to 2.9 into 5 into 6m2 plus 30. Now we need to simplify this. 2.8 into 6 into 5m2, we get this as 84m2 plus 504. On the right hand side, 2.9 into 5 into 6m2, we get 87m2 plus 2.9 into 5 into 30 is 435. Rearranging this expression, we can write 504 minus 435 is equal to 87m2 minus 84m2. So here we have 69 is equal to 3m2. So from this we can write m2 is 69 divided by 3, and this comes out to be 23. So the molar mass of the solute is 23 grams per mole. So we have found the answer for the first question. Now using this value of molar mass of solute, we will find the value of vapor pressure of water. So how we can do that? By substituting this M2 in either equation 1 or equation 2, we can calculate P1 naught, that is vapor pressure of water. So now I will substitute M2 in equation 1 to calculate P1 naught. So we have our equation 1 here. So just now we have found out the value of M2 is 23 grams per mole. This value we will substitute into equation 1 so as to find what is the value of P1 naught. So we have 2.8 divided by P1 naught, that is equal to 5 into M2, which is 23, divided by 5 into 23 plus 30. 2.8 divided by P1 naught, which is equal to 5 into 23 is 115, and in the denominator we have 5 into 23 plus 30. So that's 115 plus 30, which is equal to 145. So we need to find out P1 naught. So we will just rearrange this equation. So P1 naught is nothing but 2.8 into 145 divided by 115. So simplifying this, we get vapor pressure of water as 3.53, and the unit is kilopascal. So the vapor pressure of water at 298 Kelvin is 3.53 kilopascal, and this is how you can solve this particular question. Question number 2.20. A 5% solution by mass of cane sugar in water has freezing point of 271 Kelvin. Calculate the freezing point of 5% glucose in water if freezing point of pure water is 273.15 Kelvin. In the question, they have given us the freezing point for cane sugar in water, and they have asked us to calculate freezing point of 5% glucose solution in water. Also, they have given us the freezing point of pure water. So, by observing the freezing point of pure water, that it is 273.15 Kelvin, and the freezing point of cane sugar in water solution, we have it as 271 Kelvin. So here we observe a depression of freezing point when cane sugar is dissolved in water, and that is given by delta TF. Depression of freezing point is given by delta TF, which is 273.15 minus 271 Kelvin, and this is equal to 2.15 Kelvin. So they have asked us to calculate freezing point for 5% glucose in water. So here we will use the formula delta TF is equal to KF into M, where KF is molar depression constant and M is molality of the solution. At first, using the cane sugar in water solution, we will find what is the KF value for the solvent, that is water. In order to do that, we need to calculate what is the molality of the solution. So they have given us 5% by mass cane sugar solution is there. This means that we have 5 gram of cane sugar in 100 gram of solution. This means that we have 100 minus 5 gram of water in it. So which is nothing but we have 90 gram of water in the solution. So in order to calculate molality of the solution, we need to calculate number of moles of the solute, that is cane sugar, as well as the solvent in terms of kg we have to write. So here 95 grams of water means that it is 0.095 kg of water. So mass of solvent in kg we have written it. Now we shall calculate the number of moles of cane sugar. So number of moles of cane sugar is equal to its mass by molar mass. So mass of cane sugar, it is told that it is 5%, so mass is 5 grams divided by molar mass. So in order to calculate molar mass, we need to write the formula of cane sugar. So it is C12, H22 and O11. So we will write the molar mass here. It's 12 into 12 plus 22 into 1 plus 11 into 16. That is the atomic mass of oxygen. So further by simplifying, we have 5 divided by the molar mass of cane sugar. It comes out to be 342 grams per mole. And therefore, number of moles of cane sugar, we get it as 0.0146 moles. Now let us calculate molality of 5% solution of cane sugar in water. So therefore, molality of 5% solution of cane sugar in water, that is nothing but number of moles of cane sugar divided by volume of water in kg. So just now we have calculated the number of moles of cane sugar, that is 0.0146 moles, and volume of water in kg, since it was 95 grams, in kg it is 0.095 kg. Upon simplifying, we get molality of this solution as 0.1537. So this is the molality. Now substituting this value of molality into the expression of depression of freezing point, delta TF is equal to Kf into M. So delta TF divided by M will give us the value of the constant Kf. So Kf is equal to delta TF divided by M. And the depression of freezing point is 2.15 divided by molality of the solution is 0.1537. And this is equal to 13.99. Now coming to the unit. So here for the depression of freezing point it is Kelvin, and for molality is nothing but it is mole per kg. So the unit is Kelvin kg per mole. We have found out the value of molar depression constant for water. Now using this value of Kf, we can find out the freezing point of 5% glucose solution in water. So 5% glucose solution in water. It means that we have 5 gram of glucose dissolved in 95 grams of water. So total volume is 100 ml. Just like how we have done previously. So this 95 gram of water, it means that we have 0.095 kg of water. Glucose, its formula is C6H12O6. So the molar mass is equal to 6 into 12 plus 12 into 1 plus 6 into 16. This is equal to 180 gram per mole. This is molar mass of the glucose. Now if we calculate number of moles of glucose, is equal to its mass, that is 5 gram, divided by molar mass 180 gram. So 5 by 180 is equal to 0.0278 moles. So now using this we can calculate molality of glucose solution. Molality of glucose solution is equal to its number of moles, 0.0278 divided by volume of solvent in terms of kg. So in terms of kg, the mass of solvent is 0.095. So simplifying this, we get 0.2926. The molality of glucose solution is 0.2926 mole per kg. So now using this value of molality of the solution, and already we have calculated the value of constant, that is the molar depression constant. Using these two values, we will calculate the depression in the freezing point in case of 5% glucose solution in water. So writing the formula, delta TF is equal to Kf into molality. Now we shall use this formula for 5% glucose solution in water. we have calculated the value of Kf for water, and that was 13.99 Kelvin kg per mole. And now molality of 5% glucose solution in water, we have calculated it and we have got this as 0.2926 mole per kg. So this kg and kg inverse, mole and mole inverse gets cancelled. So we need to multiply 13.99 with 0.2926. And approximately we get this value as 4.09 Kelvin. So this is the depression in the freezing point that we have observed. So in order to calculate the freezing point of 5% glucose solution, we have to subtract this value from the freezing point of water. So subtracting that, 273.15 minus 4.09 Kelvin is equal to 269.06 Kelvin. So this is the freezing point of 5% glucose solution. Freezing point of 5% glucose solution is equal to 269.06 Kelvin. Question number 2.21. Two elements A and B form compounds having formula AB2 and AB4. When dissolved in 20 gram of benzene, that is C6H6, 1 gram of AB2 lowers the freezing point by 2.3 Kelvin, whereas 1 gram of AB4 lowers the freezing point by 1.3 Kelvin. The molar depression constant for benzene is 5.1 Kelvin kg per mole. Calculate the atomic masses of A and B. In the question, they have given us two compounds which are dissolved in benzene. And when they are dissolved in benzene separately, the freezing point will undergo depression. Also, they have given the masses of the components AB2 as well as AB4, and they have asked us to calculate atomic masses of A and B. So here, using the expression for depression and freezing point in terms of molar masses as well as masses of solute, we can calculate the molar masses. By using these molar masses, we can calculate atomic masses of A and B. Let me tell you, we have the formula for depression of freezing point in terms of molar mass of solute, that is M2 is equal to 1000 into W2 into Kf divided by delta Tf into W1. So using this formula, we can determine the molar masses of the two compounds. So here M2 means molar mass of solute. And Kf is the molar depression constant of the solvent. W2 is mass of solute, which is used to lower the freezing point of the solvent. And delta Tf represents the depression in freezing point. W1 is mass of solvent. So here we have solvent, that is benzene C6H6, and we have solute. Two compounds are given, AB2 as well as AB4. So individually for AB2 and AB4, we will find their molar masses. So using those molar masses, we can find atomic masses of A and B. So let me tell you how you can find that. Using this expression for molar masses of the solute, we will calculate molar masses of AB2. So before that, we will list the data that is given. So first, to determine molar mass of AB2, I'll write it as M AB2. So W2 is nothing but weight of that component AB2. So I'll write W2 is equal to WAB2. So that they have given 1 gram of AB2. That lowers the freezing point by 2.3 Kelvin. So here delta TF is 2.3 Kelvin. And we have W1, that is mass of benzene. So that they have given 20 gram. Also they have given the value of molar depression constant for benzene. So value of Kf is equal to 5.1 Kelvin kg per mole. Substituting all these values into the expression, I can write M AB2 is equal to 1000 into W2, that is W of AB2 is 1 gram, into the value of constant Kf, that is 5.1, divided by delta TF, it is 2.3 into W1, that is equal to 20 grams, which is equal to 110.87 gram per mole. So this is how we have calculated molar mass of AB2. In a similar manner, we will calculate molar mass of AB4. So now, similarly, to determine molar mass of AB4. So here we have weight of AB4, that is nothing but 1 gram, and the depression in freezing point delta TF when 1 gram of AB4 is added, that is 1.3 Kelvin. And the value of Kf remains same, it's 5.1 Kelvin kg per mole. And weight of benzene W1, it is 20 gram. So substituting this, we can write M AB4 is equal to 1000 into weight of solute, it's component 1, into 5.1 divided by the depression in freezing point 1.3 Kelvin into mass of benzene, that's 20. And therefore molar mass of AB4 comes out to be 196.15 gram per mole. So now we have calculated molar masses of AB2. So that is equal to 110.87 gram per mole, and that of AB4 we have calculated 196.15 gram per mole. Now here if I consider mass of atom A as X and B as Y, then I can write MAB2 is nothing but 1 into X plus 2 into Y, and this is equal to 110.87. Nothing but X plus 2Y is equal to 110.87. Similarly, for AB4, I can write 1 into X plus 4 into Y is equal to 196.15. So X plus 4Y is equal to 196.15. Let us consider these two equations as 1 and 2, and we will solve these two equations. You have studied to solve these type of equations in your high school classes. So since we have X and X in both the equations, we will change sign of these two equations and we can easily cancel them. So we are left with minus 2y, which is equal to minus 85.28. So minus and minus can be cancelled. So we get y is equal to 85.28 divided by 2, and therefore y is equal to 42.64. Now by substituting this value of y in equation 1, putting y in equation 1, so right, substitute y in 1. So we have x plus 2 into 42.64, which is equal to 110.8. By evaluating this, we get the value of x as 25.59. Therefore, we have calculated the atomic masses of A and B. So we have atomic mass of A, that is equal to x, which is equal to 25.59 U, and atomic mass of B, which we have considered as y, that is equal to 42.64 U. Question number 2.22. At 300 Kelvin, 36 gram of glucose present in a liter of its solution has an osmotic pressure of 4.98 bar. If the osmotic pressure of the solution is 1.52 bars at the same temperature, what would be its concentration? So here we need to find the concentration. First of all, we will write the mathematical expression for osmotic pressure, and we have osmotic pressure pi is equal to C into R into T, where pi is the osmotic pressure, C is the concentration, R is a constant, T is temperature. So by rearranging this expression for concentration, I can write C is equal to pi by RT. So now we will look into the question again and we will list out whatever the data that is required for us. So we need osmotic pressure here. So they have given osmotic pressure is 1.52 bars. So it is 1.52 bar. They have also given us the osmotic pressure of glucose, but for solution we need to calculate. So we will be substituting 1.52 bars as the osmotic pressure of solution. And the value of R is 0.083 bar liter per Kelvin mole. Then we need is temperature. So they have given temperature is 300 Kelvin. So C is equal to pi is 1.52 bar divided by R 0.083 bar per liter Kelvin mole inverse into temperature, that is 300 Kelvin. So simplifying the units, so bar and bar get cancelled, Kelvin inverse Kelvin gets cancelled. Simplifying the numerical values, we get 0.061, the unit is molar. So since we are asked to find concentration of the solution in liter, so this would become mole per liter, and therefore concentration is 0.061 mole per liter, which is nothing but 0.061 molar. Question number 2.23. Suggest the most important type of intermolecular attractive interaction in the following pair. We are provided with 5 different pairs here. So first is N hexane and N octane. So both are alkanes. And both are non-polar molecules. So non-polar molecules has weakest interaction among them, that is van der Waals force of attraction. So the force of attraction between N hexane and N octane is van der Waals force of attraction. The second pair we have is iodine and carbon tetrachloride. So in both iodine as well as carbon tetrachloride, both are non-polar, and therefore the type of attraction between them is also van der Waals force of attraction. The third pair is NaClO4 and water. NaClO4 can be written as Na plus ClO4 minus. So this is a ionic compound and water is a polar molecule. So whenever we have ionic compound in a polar molecule, the interaction present between them is a ion dipole interaction. So here the interaction is ion dipole interaction. So therefore, for third NaClO4 and water, the interaction we have is ion dipole interaction. Considering the fourth pair we have is methanol and acetone. Methanol is written as CH3OH and acetone is CH3COOH. So here we have hydrogen bonding between oxygen of acetone as well as hydrogen of methanol. So here we have the type of interaction is hydrogen bonding. Fifth one, acetonitrile, that is CH3CN and acetone CH3COCH3. So in the previous also it is CH3COCH3. Sorry for the mistake. So we have acetonitrile CH3CN and acetone, which is CH3COCH3. Both of these compounds can form dipoles, and therefore here we have dipole-dipole interaction. So the answer for fifth pair of compound is that they have dipole-dipole interaction. So for first and second pair, they have van der Waals force of attraction. Between NaClO4 and water, we have ion dipole interaction. Between methanol and acetone, we have hydrogen bonding. Acetonitrile and acetone, we observe a dipole-dipole interaction. Question number 2.24. Based on solute-solvent interactions, arrange the following in the order of increasing solubility in N-octane and explain. So we have the solvent given to us, it is N-octane, and we have different components that is given solute. We have cyclohexane, KCl, methanol, that is CH3OH, and we have acetonitrile CH3CN. We know that like dissolves like. What does this mean? So like dissolves like means if a solvent is non-polar. Non-polar solvent dissolves non-polar solute in it. And if we have polar solvent, it dissolves polar solute in it. So this is what I mean by like dissolves like. So now they have given us solvent N-octane. So this is an alkane which is an organic molecule, and therefore this is non-polar. So we have a solvent which is non-polar in nature. So since the solvent is non-polar, if the solute is non-polar, that dissolves non-polar solute in it. So among the given solutes, cyclohexane, KCl, CH3OH and CH3CN, cyclohexane is non-polar. KCl, CH3OH, CH3CN are polar. So now solutes, we will classify cyclohexane. We have KCl, CH3OH, CH3CN. So clearly we can tell that since cyclohexane is organic molecule, this is non-polar. Now if we speak about polarity of KCl, CH3OH, CH3CN, since KCl is an ionic compound, it is more polar than that of CH3OH, and CH3OH is more polar than acetonitrile, that is CH3CN. Cyclohexane is non-polar. Now we have a non-polar solvent and we need to arrange the solutes in the increasing order of solubility. Increasing order of solubility means one of the solute which is least soluble in the given solvent, we have to write it first. So I'll write increasing order of solubility in N-octane. So one which is highly polar, that is the least soluble in non-polar, and therefore it is KCl. KCl is least soluble. Then comes methanol, and then we have acetonitrile, and at last we have non-polar solute, that is cyclohexane, which is highly soluble in N-octane. And this is the answer for this particular question. The increasing order of solubility in N-octane is KCl lesser than CH3OH, which is lesser than CH3CN. All of these are lesser than cyclohexane. So this solubility you can explain based on the nature of solvent as well as solute. Since N-octane is a non-polar solvent, polar solutes are less soluble, and non-polar solute cyclohexane is highly soluble in N-octane. Question number 2.25. Amongst the following compounds, identify which are insoluble, partially soluble and highly soluble in water. Phenol, toluene, ethylene glycol, chloroform, formic acid and pentanol. So we need to classify or identify the given solutes which are soluble in water, partially soluble in water and which are highly soluble in water. So we have water, right? Now this is the solvent that is given to us. So first of all we need to identify whether water is a polar solvent or non-polar solvent. So we know water is polar in nature. So it is polar solvent. Now we need to identify whether the given 6 compounds are polar or non-polar. If the given compounds are polar, then it means that it is highly soluble. Okay, it is highly soluble in water. And if the given compounds are partially polar, then it means they are partially soluble. And if the given compounds are non-polar, which means that then those compounds are insoluble in water. So now we will consider given compounds one by one. And we shall identify whether it is polar, non-polar or partially polar. First we have is phenol. The formula is C6H5OH. So here we have C6H5 group and OH group. So C6H5 group is non-polar. And we have OH group which is polar in nature. So from this we can tell that since phenol is having a polar group as well as non-polar group, this is partially polar. And therefore phenol is partially soluble in water. Second compound we have is toluene. Formula is C6H5CH3. So here you can see that we have C6H5 and CH3 group which are non-polar groups. And therefore toluene as a whole is non-polar. So a non-polar compound is insoluble in water. So toluene is insoluble in water. Third is ethylene glycol. Which is OH, CH2, CH2, OH. So here we have polar groups OH, and this group can form hydrogen bonding with water. So because of this hydrogen bonding, ethylene glycol is highly soluble in water. So first three compounds, phenol, it is partially soluble in water. Toluene is insoluble in water. Ethylene glycol is highly soluble in water. Now let us discuss about chloroform, formic acid and pentanol. Fifth is chloroform. The formula is CHCl3. This is non-polar in nature. So since water is non-polar, chloroform is insoluble in water. Then we have as formic acid. The formula is HCOOH. So here we have OH group which can form hydrogen bonding. So because of the formation of hydrogen bonding, formic acid is highly soluble in water. The last compound we need to discuss, pentanol. So the molecular formula is C5H11OH. So again here we have OH group which is polar. But also we have C5H11 group which is very much bulkier. and this bulky group is non-polar in nature. As a result, pentanol is partially soluble in water. And this is the answer for the questions. Phenol is partially soluble in water. Toluene is insoluble in water. Formic acid is highly soluble in water. Ethylene glycol is also highly soluble in water. Chloroform is insoluble in water. Pentanol is partially soluble in water. Question number 2.26. If the density of some lake water is 1.25 gram per ml and contains 92 gram of Na plus ions per kg of water, calculate the molality of Na plus ions in the lake. So we are asked to calculate molality of Na plus ions. We will write the formula first. Molality of Na plus ions. So that is equal to moles of Na plus ions divided by mass of solvent in kg. So we will calculate moles of Na plus ions in the beginning. So moles of Na plus ions is its mass by atomic mass here. So it is 92 gram divided by 23 gram per mole. So 92 by 23, this comes out to be 4 moles. We will substitute this number of moles into the formula for finding molality. So we have, therefore, molality of Na plus ions, number of moles of Na plus ions, that is 4 moles, divided by mass of solvent in kg. So they have asked us to find 92 grams of Na plus ions per kg of water is present, they have given. So it is 1 kg, and therefore molality is 4 mole per kg, or I can write this as 4 molal. Question number 2.27. If the solubility product of copper sulfide is 6 into 10 to the power minus 16, calculate the maximum molarity of copper sulfide in aqueous solution. So we are provided with solubility product. So it is represented by Ks, which is equal to 6 into 10 to the power minus 16. And we are asked to calculate maximum molarity of copper sulfide in aqueous solution. So since they have given solubility product, maximum molarity is nothing but it is the solubility of copper sulfide itself. So now let us consider S as the solubility of copper sulfide in terms of mole per liter. And I can write the equation CuS can give Cu2 plus S2 minus. So if I consider S as solubility, then I can write the solubility product as KSP is equal to this concentration of Cu2 plus ions multiplied by concentration of sulfide ions. So since copper sulfide is solid, its solubility product is 1. So therefore KSP is S into S, which is equal to S square. So from this I can tell solubility is nothing but square root of its solubility product. And therefore S is equal to square root of 6 into 10 to the power minus 16, which is equal to 2.45 into 10 to the power minus 8 mole per liter. So therefore maximum molarity of copper sulfide in the aqueous solution is 2.48 into 10 to the power minus 8 mole per liter. Question number 2.28. Calculate the mass percentage of aspirin C9H8O4 in acetonitrile CH3Cl when 6.5 gram of aspirin is dissolved in 450 gram of acetonitrile. We need to find mass percentage of aspirin acetonitrile, means mass percentage of solution we have to find. So we have the formula mass percentage of solution is equal to mass of solute divided by total mass of solution into 100. So this gives us mass percentage. So here aspirin is the solute and acetonitrile is the solvent. So mass of solute, so total mass of solution is nothing but it is equal to mass of aspirin plus mass of acetonitrile CH3Cl. So mass of aspirin, they have given it as 6.5 gram and mass of acetonitrile it is 450 gram. So total mass of the solution here is 456.5 grams. Now substituting these values, mass percentage is equal to mass of solute, that is 6.5 gram of aspirin divided by mass of solution 456.5 into 100. Upon solving this, we get mass percentage as 1.424%. That's it, how you can solve this particular problem. Question number 2.29. Nalorphene, similar to morphine, is used to combat withdrawal symptoms in narcotic users. Dose of nalorphene generally given is 1.5 mg. Calculate mass of 1.5 into 10 to the power minus 3 molar aqueous solution required for the above dose. So here we are supposed to calculate the weight of solution of nalorphene that is required, which contains 1.5 mg of nalorphene. So in the given molar solution, that's 1.5 into 10 to the power minus 3 molar solution, let us find what is the amount of nalorphene that is present. Then we shall calculate the total mass of the solution. Then from that solution, to get 1.5 mg of nalorphene, how much quantity of the solution is required? Let us find the answer. We'll see how we can solve this. So first of all, they have given us, we have 1.5 into 10 to the power minus 3 molar aqueous solution of nalorphene. This means that we have 1.5 into 10 to the power minus 3 moles of nalorphene in 1 kg of water. 1 kg, I mean here it is 1000 grams. So from this we can calculate mass of nalorphene present in 1.5 into 10 to the power minus 3 molar solution. So I'll write therefore mass or amount of nalorphene present in 1.5 into 10 to the power minus 3 molar solution. This is equal to number of moles multiplied by molar mass. So I can write N into M. So this amount or mass is represented by small letter m. So this formula is just rearrangement of the formula number of moles is equal to mass by molar mass. So from this formula we have written this particular formula. Now let us calculate molar mass. So molar mass of Nalorphene. Its molecular formula is C19H22NO3. So we have 9 carbon atoms, so it is 9 into 12 plus 21 hydrogen atoms, 21 into 1 plus 1 nitrogen, 14 into 1, 1 into 14 it should be, and 3 oxygen, so 3 into 16. After solving this we get molecular weight as 311 gram per mole. Now substituting this value into the formula, M is equal to N into M. So therefore mass of Nalorphene in 1.5 into 10 to the power 3 molar aqueous solution is number of moles, that is 1.5 into 10 to the power minus 3 into its molar mass, that is 311 gram per mole, and this is equal to 0.4665 grams. So using this mass of Nalorphene as well as mass of solvent, we can calculate mass of solution. So therefore we have mass of aqueous solution, that is mass of Nalorphene added to the mass of water, mass of solvent, so that is water here. So we are supposed to add 0.4665 and 1 kg, that is 1000 grams. So we have 1000.4665 grams. So we have calculated that 0.4665 gram of Nalorphene is present in 1000.4665 grams of solution. Now for 1.5 mg of Nalorphene, how much is required? We shall calculate that. So now the mass of solution containing 1.5 mg of Nalorphene is given by 1000.4665 grams into 1.5 milligrams divided by 0.4665 grams. So this milligrams we shall convert it into grams. We have to multiply it by 10 to the power minus 3. So 1000.4665 grams into 1.5 into 10 to the power minus 3 grams divided by 0.4665 grams. So grams and grams gets cancelled. So we will be getting answer in terms of grams. Now by simplifying the numericals value, we will get 3.22 grams as the approximate value of the mass of solution, that is containing 1.5 mg of Nalorphene. Question number 2.30. Calculate the amount of benzoic acid C6H5COOH required for preparing 250 ml of 0.15 molar solution in methanol. So we should be calculating what is the amount of benzoic acid required for preparing 250 ml of solution of 0.15 molar. So first of all, we shall calculate what is the amount of benzoic acid present in 0.15 molar solution, Then we shall calculate how much amount is required for preparing 250 ml of the solution. So 0.15 molar means that we have 0.15 moles of benzoic acid, that is C6H5COOH, in 1 liter of methanol. That is, we have 0.15 moles of benzoic acid in 1000 ml of methanol. Now, how much amount of benzoic acid is present here? So I can write, therefore, mass of benzoic acid in 1000 ml of 0.15 molar solution is nothing but its mass, that is molar mass, multiplied by number of moles. So now let us calculate molar mass of benzoic acid. Molar mass of C6H5COOH is equal to 6 into 12 plus 5 into 1. So one more carbon atom is there. So it is 7 into 12 plus 5 into 1 plus 2 into 16. That's equal to 122 grams per mole. So let us substitute. Therefore, mass of benzoic acid in 1 liter, that is 1000 ml of 0.15 molar solution, is equal to 122 into number of moles, that is 0.15 moles. So this is equal to 18.3 grams. And therefore, mass of benzoic acid required to prepare 250 ml of 0.15 molar solution. So how we can calculate? For 1000 ml, we require 18.3 grams of benzoic acid. So for 250 ml, what is the quantity of benzoic acid that is required? So we have 250 ml into 18.3 grams divided by 1000 ml. Milliliters gets cancelled. So the unit is in terms of grams because we need to represent mass of benzoic acid. Simplifying the numerical values, 250 into 18.3 divided by 1000, which is equal to 4.575 grams. So in order to prepare 250 ml of 0.15 molar solution of benzoic acid in methanol, we require 4.575 grams of benzoic acid. Question number 2.31. The depression in freezing point of water observed for same amount of acetic acid, trichloroacetic acid and trifluoroacetic acid increases in the order given above. Explain briefly. So they have given us that when we take same amount of acetic acid, trichloroacetic acid and trifluoroacetic acid, it is observed that the depression in freezing point for water is increasing in the order that is given. Means it is greater for trifluoroacetic acid than that of trichloroacetic acid and it is lowest for acetic acid. Now we are supposed to explain why this is observed. Let me write the structure of all these three acids and then we shall try to explain the reason for observing this order in the depression in freezing point of water. So acetic acid, it is CH3COOH. So C, 3 hydrogens, COOH. This is how we can represent it. Trichloroacetic acid, CCl3COOH. And trifluoroacetic acid means we have 3 fluorine atoms attached to carbon atom. So in case of acetic acid, we have hydrogen, and in case of chloroacetic acid, we have chlorine, and in case of trifluoroacetic acid, we have fluorine. So among these 3 groups, that's hydrogen, chlorine and fluorine, hydrogen is least electronegative. Electronegativity of hydrogen is least. And among these 3, fluorine is most electronegative. Means when we compare hydrogen, chlorine and fluorine, fluorine can attract shared pair of electron towards it more than that of hydrogen as well as chlorine. So this fluorine withdraws more electron towards itself compared to chlorine and hydrogen. So because of which this carbon will get a positive charge. As a result, this carbon atom will take electrons from the neighboring carbon atoms, and this carbon, it will take it from oxygen. So the COOH I can write as COOH. As a result of which it can give hydrogen ion easily. So H plus from the trifluoroacetic acid can be given out very easily. So I can tell trifluoroacetic acid ionizes to a larger extent. It means that more number of ions are produced in case of trifluoroacetic acid, as a result of which the depression of freezing point will be greater. Now if we compare trichloroacetic acid as well as trifluoroacetic acid, trichloroacetic acid, the release of H plus ions is somewhat lesser compared to that of trifluoroacetic acid. As a result, the decrease in the freezing point will be less when compared to that of trifluoroacetic acid. And in case of acetic acid, the ionization, the extent to which ionization is taking place is much lesser compared to that of trichloro as well as trifluoroacetic acid. As a result, the depression of the freezing point will be much lesser than that of the other 2 cases. So here you can answer that among hydrogen, chlorine and fluorine, electronegativity of fluorine is most and electronegativity of hydrogen is least. As a result, fluorine can withdraw electrons towards itself more than chlorine and hydrogen. As a result of this, trifluoroacetic acid can easily lose H plus ions. Since the ionization of trifluoroacetic acid is taking place to a larger extent, more ions are produced, and as a result of this, greater is the depression of freezing point, and therefore the depression in freezing point increases in the order acetic acid, trichloroacetic acid and trifluoroacetic acid. Let's move into the next question. Question number 2.32. Calculate the depression in the freezing point of water when 10 gram of CH3CH2 CHCl COOH is added to 250 gram of water. Ka is equal to 1.4 into 10 to the power minus 3. Kf is equal to 1.86 Kelvin kg per mole. So in the question we are asked to calculate the depression in the freezing point when a carboxylic acid, that's given here, a carboxylic acid is added to water. So here, since they have given us a compound which is undergoing dissociation when it is added to water. So the expression for depression in the freezing point will be delta TF is equal to I KF into M. Van 't Hoff factor I is included in the expression for the depression of freezing point. It is because the given compound is undergoing dissociation when it is added to water. So now the value of Kf that is given to us in the question, so which is equal to 1.86 Kelvin kg per mole. Also they have given us the value of dissociation constant Ka, 1.4 into 10 to the power minus 3. Now we need to calculate the value of Van 't Hoff factor I as well as molality. Then after finding these two values, we can calculate the value for depression in the freezing point. Let us calculate molality of the solution and then let us calculate the value of Van 't Hoff factor, and then finally we will substitute into the expression of depression of the freezing point. So let us calculate molality. So calculation of molality of the solution. So molality is nothing but it is number of moles of the solute per kg of the solvent. So we shall find the number of moles of the solute. So in order to find number of moles, we require molar mass. So first of all, let us calculate molar mass of the given component, that is CH3, CH2, CHCl, COOH. So here we have 4 carbon atoms. So it is 4 into 12. And we have 3 plus 2 plus 1 hydrogen atom. So 7 into 1. Plus we have 1 chlorine atom, 1 into 35.5, and we have 2 oxygen atoms, 1 into 35.5 plus 2 into 16, which is equal to 122.5 gram per mole. So now let us calculate number of moles. So they have given us mass of CH3, CH2, CHCl, COOH. This is equal to 10 grams, and therefore number of moles is equal to mass by molar mass. So it is 10 grams divided by 122.5 grams per mole, and this is equal to 0.0816 moles. So using this we can calculate molality of the solution, and therefore molality is equal to number of moles of solute, which is 0.0816 moles, divided by mass of solvent in kg. So here they have given us that it is added to 250 grams of water. So 250 is given in terms of grams. So we have to convert it into kg. So that would be 0.25 kg, or I can write 250 divided by 1000 kg. So which is equal to 0.0816 mole divided by 0.25 kg, which is equal to 0.3264 molal, that is mole per kg, or I can write 0.3264 m. Now let us calculate the value of Van 't Hoff factor, that is I. In order to calculate I, let us consider the dissociation of the given carboxylic acid. So it can be written as CH3, CH2, CHCl, COOH, and it gives CH3, CH2, CHCl, COO minus and H plus ions. After some times, an equilibrium will be established between that of the compound as well as its ions. Now, when time is 0, that is initially, let us consider the concentration of the acid as C moles per liter. During that time, ions will not be formed, so the concentration of ions will be 0 molars. Now at equilibrium, when time is attained such a way that there is equilibrium, then let us consider alpha moles of ions will be formed in the solution. So during the equilibrium, the concentration of acid will be 1 minus alpha moles per liter. So since we have C number of ions here, the concentration will be C into 1 minus alpha. So from this equation, we can write the expression for dissociation constant Ka, which is equal to, so the concentrations here will be C alpha and C alpha. So it is C alpha into C alpha divided by C into 1 minus alpha. So 1 C gets cancelled. We are left with C into alpha square divided by 1 minus alpha, which is nothing but the value of Ka. Now, since alpha is very less compared to 1, we can write 1 minus alpha is approximately 1, and therefore I can write Ka is equal to C into alpha square, or I can write alpha square is equal to Ka divided by C. From this I can write alpha is nothing but square root of Ka divided by C. The value of dissociation constant is given to us in the question, that is 1.4 into 10 to the power minus 3 divided by the concentration, which we have found out as molality of the solution. It is 0.3264. Square root of simplified value will give us the value of alpha, and that is equal to 0.0655. So we have calculated the value of alpha, that is the degree of dissociation. Now using the value of degree of dissociation, let us calculate the value of I. Again, if I consider the dissociation of the acid, I can write the same equation, CH3, CH2, CHCl, COOH. And this gives the ions CH3, CH2, CHCl, COO minus and H plus. So after some time, equilibrium will be attained. Okay. So initially, when time is 0, let us consider we have 1 mole of acid and the number of ions formed will be 0 moles. At equilibrium, if alpha moles of the ions are formed, then the concentration of the acid which originally taken will be 1 minus alpha. Now, total moles that is present at equilibrium is given by adding up the concentrations of ions as well as the acid at the equilibrium. So this is equal to 1 minus alpha plus alpha plus alpha. So alpha plus alpha and minus alpha gets cancelled. We are left with 1 plus alpha. Now we know that Van 't Hoff factor I is the ratio of change in concentration to the original concentration. So we have the observed change in concentration is 1 plus alpha, whereas the original number of moles that is present is 1. So I is 1 plus alpha divided by 1, which is equal to 1 plus alpha. So we have I is equal to 1 plus the value of alpha is 0.0655. So I is equal to 1.0655 5. So now we have found out the value of Van 't Hoff factor I, and previously we have determined the value of molality. So using these two values, we can calculate the depression in the freezing point of water. So therefore we can write delta TF is equal to, the formula it's I KF into M. I we have calculated, it's 1.0655, and the value of KF it's 1.86 Kelvin kg per mole, and molality is 0.3264 mole per kg. After simplifying this, we get the value of depression in the freezing point for water is 0.65 Kelvin. Question number 2.33. 19.5 gram of CH2FCOOH is dissolved in 500 gram of water. The depression in the freezing point of water observed is 1 degree centigrade. Calculate the Van 't Hoff factor and dissociation constant of fluoroacetic acid. In the question, we are provided with weight of fluoroacetic acid, weight of water. Also, they have given us the depression in the freezing point that is observed. So, using all these values, we can calculate the observed molar mass of the fluoroacetic acid in the given solution. So, we can calculate the molar mass of fluoroacetic acid using its formula. So, using these two values, we can calculate Van 't Hoff factor, that is the ratio of observed molar mass to that of calculated molar mass will give us Van 't Hoff factor. Then by finding the value of degree of dissociation, we can calculate the value of dissociation constant for fluoroacetic acid. So now let's proceed with the calculation. In the question, they have given that 19.5 gram of fluoroacetic acid is dissolved in 500 gram of water. So we have W1, that's weight of water, 500 grams. W2 is weight of fluoroacetic acid, that is 19.5 grams. They have given us the observed value of depression in freezing point, that is 1 degree centigrade or 1 Kelvin I can write. Also we know the value of KF for water, it is 1.86 Kelvin kg per mole. Now we have the formula to calculate molar mass of fluoroacetic acid. M2 is equal to KF into W2 into 1000 divided by delta TF into W1. So let's substitute all these values into the formula. KF is 1.86 Kelvin kg per mole. W2 is 19.5 gram into 1000 divided by delta TF, that is 1 Kelvin, into W1, which is 500 grams. After simplifying this, we get the value of M2 as 72.54 grams per mole. So this is the value of observed molar mass of fluoroacetic acid. So I can write observed molar mass of CH2F COOH. So I'll write this as M2OBS for observed, which is equal to 72.54 grams per mole. So now let us calculate the molar mass of fluoroacetic acid. So I'll write calculated molar mass of fluoroacetic acid. So this calculation is by considering its formula. So I'll write M2 calculated. It's equal. We have 2 carbon atoms. So 2 into 12, it's 24. And we have 3 hydrogen atoms. So plus 3. 1 fluorine atom plus 19. And we have 2 oxygen atoms. So 16 into 2, that is 32. Which is equal to 78 grams per mole. Van 't Hoff factor I is the ratio of calculated molar mass to the observed molar mass. So M2 calculated divided by M2 observed. So which is equal to 78 grams per mole divided by 72.54 grams per mole. And this is equal to 1.0753. So we have calculated Van 't Hoff factor, which is equal to 1.0753. Now by considering the dissociation of fluoroacetic acid and using the value of Van 't Hoff factor, we shall calculate the degree of dissociation of the acid, using which we will calculate the dissociation constant. So let us consider the dissociation. CH2F COOH. So we'll dissociate to give ions CH2F COO minus and H plus ions. So let us consider alpha as the degree of dissociation. Now initially when time t is 0, let us consider we have C mole per liter of the acid, which will not ionize, so the concentration of ions will be 0. Now when the time is attained such a way that equilibrium is attained between the acid as well as its ions, let alpha number of moles of ions be formed. Then the concentration of the acid at the equilibrium point of time will be 1 minus alpha. So since we have C moles of concentration initially, so C alpha moles of ions will be formed and the concentration of acid at equilibrium will be C into 1 minus alpha. So we have total moles at equilibrium, sum of concentrations of fluoroacetic acid as well as the ions that is formed after dissociation. So we have C into 1 minus alpha plus C alpha plus C alpha. We can simplify this, C into C minus alpha plus C alpha plus C alpha. So at equilibrium we have total moles is C into 1 minus alpha. Sorry, this should be plus. So we have total number of moles, that is C into 1 plus alpha. So therefore we can write I is C into 1 plus alpha divided by C, which is equal to 1 plus alpha. From this we can write alpha is I minus 1, which is equal to 1.0753 minus 1, which is equal to 0.0753. And therefore we have calculated alpha, which is equal to 0.0753. Now for the equilibrium which we have represented here, the expression for dissociation constant is given by Ka is equal to CH2F COO minus its concentration into concentration of H plus ion divided by the concentration of fluoroacetic acid. So we have considered the concentration of the ions as C alpha at equilibrium. So this is C alpha into C alpha divided by C into 1 minus alpha. Therefore we have Ka is equal to C into alpha square divided by 1 minus alpha. Now let us find what is the concentration of the solution, and we shall substitute into this formula along with the value of alpha so as to calculate the dissociation constant. So as to find concentration of the solution, since we have considered the concentration of the acid as well as ions in terms of mole per liter, we will calculate concentration of solution in terms of molarity. So they have given us, we have 500 grams of water. So since the density of water is 1 gram per ml, we can consider this is equivalent to 500 ml of water. We need to calculate number of moles of fluoroacetic acid. So number of moles of CH2F COOH is its mass divided by molar mass. Mass is given to us in the question. It's 19.5 grams. Molar mass we have calculated, that is 78 grams per mole. And therefore, number of moles of fluoroacetic acid is 0.25 moles. Now we shall calculate concentration in terms of molarity. Therefore, molarity of the solution is equal to number of moles of solute divided by volume of solution in liter. So number of moles is 0.25 moles divided by volume of solution in liter. That is in terms of milliliter, that is 500 divided by 1000 liter it is. So simplifying this, we get molarity of the solution as 0.5 molar. Now let us substitute the value of molarity as well as alpha into the expression of Ka, that is C alpha square divided by 1 minus alpha. So we have C, that is 0.5 molar into square of alpha, that is 0.0753 squared divided by 1 minus 0.0753. This is equal to 0.5 into 0.00567 divided by 0.9247, which is equal to 0.00307. This we can write it as 3.07 into 10 to the power minus 3. And therefore, the value of dissociation constant of the acid is 3.07 into 10 to the power minus 3. Question number 2.34. Vapor pressure of water at 293 Kelvin is 17.535 mmHg. Calculate the vapor pressure of water at 293 Kelvin when 25 grams of glucose is dissolved in 450 grams of water. We shall make use of Raoult's law here to calculate the vapor pressure of water when glucose is dissolved in it. So we will be using the formula P1 naught minus P1 divided by P1 naught is equal to Chi2, that is N2 divided by N1 plus N2. So let us write down the data that is given to us and we shall convert that into the required form so as to substitute into the formula and we shall find the answer. So we are provided with vapor pressure of water at 293 Kelvin, that is vapor pressure of pure water is given. So P1 naught is equal to 17.535 mmHg. Also they have asked us to calculate what is P1, that is when 25 grams of glucose is dissolved in 450 gram of water. So we are provided with mass of glucose, that is W2 is equal to 25 grams. We are provided with weight of water, that is W1, which is equal to 450 grams. In order to calculate the number of moles N1 and N2, we shall calculate molar mass of glucose as well as water. So write molar mass of glucose that is C6H12O6. So this is M2, which is equal to 6 into 12 plus 12 into 1 plus 6 into 16. So that is equal to 180 grams per mole. Similarly, we have molar mass of water M1, which is equal to 18 grams per mole. So now let us calculate the number of moles of glucose as well as number of moles of water. So number of moles of glucose, that is N2 is equal to its mass by molar mass. So mass we have is W2 divided by molar mass M2. So we have W2, that is 25 grams. Molar mass is 180 grams per mole. Simplifying this, we get the number of moles of glucose as 0.139 moles. Similarly, we can calculate number of moles of water. N1 is equal to W1 divided by M1, which is equal to 450 divided by 18, which is equal to 25 moles. Now let us substitute all these values into the formula. P1 naught, which is 17.535 minus P1 divided by 17.535, which is equal to N2, that is 0.139 divided by N1, which is 25 plus 0.139. From this we can write 17.535 minus P1 is equal to 0.139 into 17.535 divided by 25 plus 0.139 is 25.139. 17.535 minus P1 is equal to, simplifying the numericals on the right hand side, we get 0.097, and therefore we can write P1 is equal to 17.535 minus 0.097. This is equal to 17.44, and the unit is mmHg. So therefore, we have the vapor pressure of water is 17.44 mmHg. Question number 2.35. Henry's law constant for the molality of methane in benzene at 298 Kelvin is 4.27 into 10 to the power 5 mmHg. Calculate the solubility of methane in benzene at 298 Kelvin under 760 mmHg. Here they have asked us to calculate the solubility of methane in benzene. This solubility here means we are supposed to calculate the mole fraction. So we shall make use of Henry's law here. So we have the expression P is equal to KH into chi. So here chi is what we need to determine, and that will tell us about the solubility. So we are given that Henry's law constant, that is KH, is equal to 4.27 into 10 to the power 5 mmHg. So they have given us the value of pressure P, that is 760 mmHg. So therefore, from Henry's law, that is from this equation, P is equal to KH into chi, we can write chi is equal to P divided by KH, and therefore we have 760 mmHg divided by 4.27 into 10 to the power 5 mmHg. So this is equal to 177.99 into 10 to the power minus 5. So this can be approximately written as 178 into 10 to the power minus 5. So therefore, the mole fraction of methane in benzene is 178 into 10 to the power minus 5. And this is the answer for this particular question. Question number 2.36. 100 gram of liquid A with molar mass 140 grams per mole was dissolved in 1000 grams of liquid B, whose molar mass is 180 grams per mole. The vapor pressure of pure liquid B was found to be 500 torr. Calculate the vapor pressure of pure liquid A and its vapor pressure in the solution if the total vapor pressure of the solution is 475 torr. So here we are asked to calculate the vapor pressure of pure liquid A. Means P naught for A is what we have to calculate, and also its vapor pressure in the solution. PA also we need to calculate, and they are provided with certain data, that is total vapor pressure is given. So I'll write P total, that is given, it is 475 torr. Also they have told us we have 100 gram of liquid A. So therefore I can write W of A, which is 100 gram, whose molar mass is 140 grams per mole. MA is 140 grams per mole, which was dissolved in 1000 gram of liquid B. So I can write WB is 1000 grams, whose molar mass MB is equal to 180 grams per mole. The vapor pressure of pure liquid B, so they have given us P naught B, which is 500 torr. So these data they have given us, and we need to find P naught A, PA. So what we can do here is, first of all, we can find the value of PV. So using Raoult's law, we can find the value of PV. Then by using the value of total pressure, we can find the value of PA. So let me write the expression here. So we have PV is equal to P naught of B into chi B. So using this expression, we can find what is PV. Then we will use the expression P total is equal to PA plus PV, using which we can find the value of PA. Now using the expression PA is equal to PA naught chi A, we can find the value of P naught. So let us make use of these three equations to find the answer that is required for this particular question. So first of all, let us use equation 1 to find PV. Using equation 2, let us find PA. Using this equation 3, we shall find P naught A. So let us proceed one by one. First of all, we shall find the value of PV, for which we require the value of chi B. Similarly, to use equation 3, we need the value of chi A. So let us find the value of mole fractions for liquid A as well as liquid B. In order to calculate mole fractions, first of all, we should be calculating the number of moles of A as well as B. So let us start with the calculation of number of moles. So let us find number of moles for liquid A. So number of moles of liquid A, that is Na, is equal to its mass by molar mass. So I have written Wa by Ma, which is equal to 100 grams divided by 140 gram per ml. So the number of moles is equal to 0.714 mole. Similarly, number of moles of B, that is Nb, is equal to Wb divided by Mb. So mass of liquid B is 1000 grams divided by its molar mass is 180 grams per mole. So the number of moles is 5.556 moles. So now let us calculate mole fraction of A. So mole fraction of A, that is chi A, is equal to Na divided by Na plus Nb. So this is equal to 0.714 divided by 0.714 plus 5.556. After simplifying, we get the mole fraction of A as 0.114. So the mole fraction of B, that is chi B, which is equal to 1 minus chi A, which is equal to 1 minus 0.114, which is equal to 0.886. So now using equation 1, that is PB is equal to P naught B into chi B, we can calculate the value of PB. So P naught B is 500 torts into chi B, which we have calculated just now, 0.886, and this is equal to 443 torts. So the value of PB we have calculated. For your reference, I'll write from equation 1. So PB is 443 torts. Now using equation 2, that is by using the expression for total pressure, we shall calculate the value of PA. So now we have P total is equal to PA plus PB. So from this we can write PA is equal to P total minus PB. So we are provided with P total, that is 475 torr. So this is 475 minus PB, that is 443. And therefore the value of PA will be 32 torts. Now we need to find the value of PA naught. So we can use PA is equal to PA naught into chi A. So from this we can write P naught A is equal to PA divided by chi A. So PA is 32 torr divided by mole fraction of A, 0.114, and therefore value of P naught of A is 280.7 torrs. So the vapor pressure of pure liquid A is 280.7 torrs. Question number 2.37. Vapor pressures of pure acetone and chloroform at 328 Kelvin are 741.8 mmHg and 632.8 mmHg respectively. Assuming that they form ideal solution over the entire range of composition, plot P total, P chloroform and P acetone as a function of chi acetone. Experimental data observed for the different composition is tabulated. Also plot this data on the same graph paper. Indicate whether it has positive deviation or negative deviation from the ideal solution. So when we plot this data that is given here in a graph, we will get a graph like this. When P acetone and P chloroform is plotted as a function of chi acetone, we get two curves like this. Also, when we add pressure of chloroform and the pressure of acetone, we get total pressure. So this total pressure is also plotted here. So when we see this curve for total pressure, the curve is downwards. So this downward curve tells us that it shows a negative deviation from the ideal solution. So I can write plot of P total of the solution has a downward curve. So therefore, we can tell that the solution shows negative deviation from the ideal behavior. So this is the answer for this particular question. Question number 2.38. Benzene and toluene form ideal solution over the entire range of composition. The vapor pressure of pure benzene and toluene at 300 Kelvin are 50.71 mmHg and 32.06 mmHg respectively. Calculate the mole fraction of benzene in vapor phase if 80 gram of benzene is mixed with 100 gram of toluene. So we are provided with the vapor pressure of pure benzene. So let me write this as P naught B, which is equal to 50.71 0.71 mmHg and that of pure toluene. So I'll write it as P naught T, that is equal to 32.06 mmHg. Also they have given us the weight of benzene. So let me write this as WB, which is 80 gram, and toluene WT, that is 100 grams. So we need to find the mole fraction of benzene in vapor phase. So means PB divided by PB plus PT is how much is what we need to find. So here we will make use of the expression PB is equal to P naught B into chi B to find the value of PB, and PT is equal to P naught T into chi T to find the value of PT. Later on we will substitute into this equation to find the value of mole fraction of benzene in vapor phase. So this is mole fraction of benzene in vapor phase. So first of all, let us find what is mole fraction for toluene as well as mole fraction for benzene. So in order to find mole fraction, we need to calculate the number of moles for benzene as well as toluene. So let us find the number of moles. We shall start with finding molar mass of benzene, that is C6H6. So 6 into 12 plus 6 into 1, which is equal to 78 grams per mole. Similarly, molar mass of toluene, that is C6H5CH3, which is equal to 7 into 12 plus 8 into 1, that is 92 grams per mole. So using the molar mass, now we can calculate number of moles of benzene in 80 grams. So the number of moles of benzene, I'll write this as NB, number of moles of benzene, which is its mass, means WB divided by molar mass of benzene. So molar of mass of benzene, I'll write this as MB, and that of toluene, I'll write this as MT. So WB is 80 grams divided by MB, that is 78 grams per mole, and therefore number of moles of benzene is 1.026 moles. Similarly, let us calculate number of moles of toluene. Number of moles of toluene, NT is equal to WT divided by MT. So it's given that 100 gram of toluene is there. Its molar mass is 92, and therefore the number of moles is 1.087 moles. Now we shall calculate the mole fraction for benzene. So mole fraction of benzene, that is chi B, is equal to NB divided by NB plus NT, which is equal to 1.026 number of moles of benzene divided by 1.026 plus 1.087. This is equal to 0.486. So same way, mole fraction of toluene, so chi T is nothing but 1 minus chi B, which is equal to 0.1 minus 0.486, that is equal to 0.514. Now we have the partial pressures of pure benzene and toluene that is given to us. Already we have listed. P naught B, that is equal to 50.71 mmHg, and that of pure toluene 32.06 mm Hg. So using these two, now we shall calculate the partial vapor pressure for benzene as well as toluene. So we have Pb, that's equal to P0B into chi B, which is equal to 50.71 into value of chi B, that is 0.486. So the partial vapor pressure of benzene is equal to 24.645 mm Hg. So similarly, we have partial vapor pressure of toluene, that's equal to P0T into chi T, which is equal to 32.06 mm Hg into mole fraction, that's 0.514, and therefore the partial vapor pressure for toluene is 16.479 mm Hg. So now we have calculated the partial vapor pressures for benzene as well as toluene. So using this, we can calculate mole fraction of benzene in vapor phase. Mole fraction of benzene, that is C6H6, in vapor phase. So that's equal to Pb divided by Pb plus Pt, that's partial vapor pressure of toluene. So we have 24.645 divided by 24.645 plus 16.479, which is equal to 24.645 divided by 41.124, and this is equal to 0.599. So approximately we can write this as equal to 0.6. So this is the mole fraction of benzene in its vapor phase. Question number 2.39. The air is a mixture of number of gases. The major components are oxygen and nitrogen with approximate proportions of 20% is to 79% by volume at 298 Kelvin. The water is in equilibrium with air at a pressure of 10 atmosphere. At 298 Kelvin, if the Henry's law constant for oxygen and nitrogen at 298 Kelvin are 3.30 into 10 to the power 7 mm and 6.51 into 10 to the power 7 mm respectively, calculate the composition of these gases in water. So in the question, we are provided with the percentage composition of air and nitrogen. So we have 28% of oxygen and 79% nitrogen in air. Also they have given Henry's law constant for oxygen and nitrogen. So K H for O2 they have given. So that's equal to 3.30 into 10 to the power 7 mm. And for nitrogen, they have given 6.51 into 10 to the power 7 mm Hg in terms of mercury pressure they are telling it. So we are asked to calculate the composition of the gases in water. So using Henry's law, we have P is equal to KH into chi. So making use of this formula, we need to calculate composition. Means here we need to calculate what is the value of chi for oxygen as well as for nitrogen in water. Also in the question, they have given that water is in equilibrium with air at a pressure of 10 atmosphere. So we know 1 atmosphere is 760 mm Hg. Now they are told it is at 10 atmosphere, water is at equilibrium. Means in terms of mercury pressure, it is 10 into 760 mm Hg, and that's 7600 mm Hg. So it is at this pressure water is in equilibrium with air. So now, using this data, we can calculate the partial vapor pressure for oxygen. So the partial pressure for oxygen can be denoted as PO2. Now since 20% of oxygen is present in air, so it is 20 divided by 100 into 7600 mm Hg. Upon simplifying this, we get the partial pressure for oxygen as 1520 mm Hg. Similarly, we can calculate the partial pressure for nitrogen gas. So the partial pressure for nitrogen PN2, that is equal to, it is told it is present in 79%. So 79 divided by 100 into 7600 mm Hg. So this comes out to be 6004 mm Hg, which is the partial pressure of nitrogen gas. Now we will make use of Henry's law, that is the expression P is equal to Kh into chi, and we will find the value of chi for oxygen as well as nitrogen separately. That will give us the required answer. So for oxygen, I can write PO2 is equal to Kh chi O2. So rearranging this, I can write chi O2 is equal to PO2 divided by the Kh value for oxygen. Substituting the values, PO2 is 1520 mm Hg divided by the value of Kh for oxygen, it is 3.30 into 10 to the power 7 mm Hg. Simplifying this, we get mole fraction of oxygen is 4.61 into 10 to the power minus 5. Similarly, for nitrogen, we can write PN2 is equal to Kh chi N2. Rearranging this, we can write mole fraction of nitrogen is partial pressure of nitrogen divided by Henry's constant for nitrogen. So PN2 is 6004 mm Hg divided by Henry's law constant for nitrogen, it is 6.51 into 10 to the power 7 mm Hg. Simplifying this numerical values, we get the mole fraction for nitrogen is 9.22 into 10 to the power minus 5. So this is how we can answer this particular question. Question number 2.40. Determine the amount of CaCl2 with I value 2.47 dissolved in 2.5 liters of water such that its osmotic pressure is 0.75 atmosphere at 27 degrees centigrade. We are asked to find the amount of calcium chloride. Okay. So they have given us volume of solution. So volume is given. Volume V is equal to 2.5 liters. Okay. Osmotic pressure is given. So pi is equal to 0.75 atmosphere. Temperature is given, that is 27 degrees centigrade, which is equal to 27 plus 273 Kelvin, which is equal to 300 Kelvin. So we have the formula for osmotic pressure, that is pi is equal to, also they have given the value of I, this 2.47. So we have the formula pi is equal to I CRT, where C is concentration, can be written as N by V into RT. So this number of moles is nothing but mass by molar mass. So I can write I into M divided by M into V into R into T. So we will make use of this formula to determine the amount of calcium chloride that is dissolved in 2.5 liter of water. So we know that the value of R is 0.0821 liter atmosphere per Kelvin per mole. W is what we have to calculate. Other than that, molar mass for calcium chloride we have to calculate. So this is equal to 40 for calcium and 2 into chlorine atoms, 2 into 35.5. So this is equal to 111 gram per mole. So let us substitute all these values into the formula. Let me just rearrange this. So in order to get M, the formula is pi into M into V divided by I into R into T. So now substituting all the values, therefore amount of CaCl2. So that is M is equal to the value of pi, that is 0.75 atmosphere into molar mass 111 and volume, it is 2.5 liters, divided by I 2.47 into R 0.0821 into temperature, that is 300. After simplifying this, we will get the weight as 3.42 grams. And therefore, the required amount of calcium chloride is 3.42 grams. Question number 2.41. Determine the osmotic pressure of a solution prepared by dissolving 25 milligrams of K2SO4 in 2 liters of water at 25 degrees centigrade, assuming that it is completely dissociated. So here they have asked us to determine osmotic pressure. So the formula to determine osmotic pressure is pi is equal to CRT. But they have given us an ionic compound K2SO4 and they have asked us to assume that it is completely dissociated. So since they have mentioned us about dissociation, we have to consider Van 't Hoff factor. So the formula is pi is equal to ICRT. So since concentration is not given directly, it's given in terms of liters, we can write concentration as number of moles divided by volume. So C is N by V I can write. So the formula is pi is equal to I into N by V into RT. So number of moles we can calculate by dividing the mass by molar mass. So substituting this formula for number of moles in the formula for osmotic pressure, I can write pi is equal to I M divided by molar mass into volume into R into T. So we shall make use of this particular formula to find the osmotic pressure. So mass is given to us. M is 25 milligrams, that is 25 into 10 to the power minus 3 grams. Volume is given, it is 2 liters. Temperature is given 25 degrees centigrade. So we have 25 plus 273, that's equal to 298 Kelvin. And we have the value of R, which is equal to 0.0821 liter atmosphere per Kelvin mole. Molar mass, that is M, for K2SO4 is equal to 2 into atomic mass of potassium, that is 39, plus 1 into atomic mass of sulfur, that's 32, plus 4 into atomic mass of oxygen, and this is equal to 174 grams per mole. Now we need to determine I. So let us consider the dissociation of K2SO4. It's told that it is undergoing complete dissociation. So we get K plus and SO4 2 minus ions. So we have 2 potassium atoms in the left hand side. So we shall balance the equation. So it is 2K plus and SO4 2 minus. So the total number of ions produced here will be 2 plus 1, 2 K plus ions and 1 SO4 ions. So total ions produced is equal to 2 plus 1, that is 3. And therefore, the value of Van't Hoff factor here is I is equal to 3. Now we shall substitute all these values into the expression for osmotic pressure. Pi is equal to 3 into M is 25 into 10 to the power minus 3 into R 0.0821 into temperature, that is 298, divided by molar mass, that is 174, into volume, that is 2 liters. After simplifying this, we will get the osmotic pressure as 5.27 into 10 to the power minus 3, and the unit is atmosphere.